about Gibbs temperature convergence of Gibbs measured for the locally finite potential in two-dimensional.
Okay, thank you, Rodrigo, for the introduction.
Actually, 1 minute.
1 minute.
Okay, no, it's okay.
So Rodrigo knows very well this work. It's a joint work with Sébastien Barbieri, Rodrigo Bisacco, and Gregorio Dale-Vedov, and actually it's part of the thesis of Gregorio. Okay, so first I will discuss the problem, and then what is new in dimension 1, and actually we are going to prove and extend this in dimension 2. Okay, so this is the problem. So we want to understand a notion that was introduced by Van Enter and Russell, 2007, which is called the zero temperature chaotic convergence. So I will be more precise later, but we start with a spin system, lattice spin system of a finite alphabet, and a function phi which will be the Hamiltonian on the site 0, and any Gibbs measure associated to this Hamiltonian at temperature beta that I call mu beta phi. So the question is, what is the limit of mu beta phi when beta goes to infinity, when the temperature goes to 0? But the problem is that the set of Gibbs measures is large. So the question is really, what is the limit of a set of a Gibbs measure when the temperature goes to 0? So the phenomenon, what is called by Van Enter zero temperature chaotic convergence, means that there exist two disjoint sets on the K0 and K1, so that if you take any Gibbs measure and there exists a subsequence of temperature, beta k, okay, it's here. There exists a subsequence of temperature and two disjoint compensates, such that if I take any invariant Gibbs measures associated to the temperature beta k, then if I choose k even, 2k, then the measure, the limit of the measure exists and is supported on k0. If I take k even, 2k plus 1, then the measures, all the Gibbs measures converges to k1. So it's the whole set which converges to k0 or the whole set which converges to k1. So there is an oscillating behavior at some specific sequence of temperature. That's what means chaotic convergence. Of course, you cannot take any subsequence, beta k, because by compactness, there always exists a subsequence so that the convergence exists for some new beta. So in the previous definition, you cannot say that for every subsequence, the whole set converges to two disjoints, has to disjoint set of the measures with disjoint support. So that's not possible. But there is an extension of the definition that has been done by Coronel, Rivera, Letelier, and they say something about every convergence, every subsequence. So for every subsequence of temperature, but then you have to perturb a little bit. So there exists a small perturbation for every epsilon. There is a small perturbation such that now the Gibbs measures, maybe I forgot mu, no, such that for, so there exists a perturbation and a subsequence of temperature with respect to the perturbation psi, so that if I take now any Gibbs measure at this subsequence of temperature for psi, then this satisfies is chaotic according to Van Enter. So for k odd, it goes to the whole set goes to support to some support of measures, and for k even it goes to another support which is this joint. So actually we don't do this. So we don't extend Van Enter in this direction, but actually the whole method is very robust, so that there would be a possibility to do this. So that's a stronger notion. I will not discuss this. I just wanted to recall Coronel, Rivera, Letelier. Okay, now a general setting, so let's be more precise. So we discuss a spin system over a finite alphabet, and then we take the full shift here, so the full set of configuration. So we are discussing invariant Gibbs measures, so not just Gibbs measures, so invariant Gibbs measures. So we introduce the space of translation, and here also it's not a conventional way to define the Hamiltonian, but we use just one function, which means it's the contribution of the whole interaction energy at the side 0. So if you want to compute now the Hamiltonian of a box, you just sum over all sides in the box K by translating the function phi. So it's the way we define the Hamiltonian of a box lambda. But actually there is a remark that usually we define family of interaction. Here we will be discussing only interaction of short range, so of size d. So usually the Hamiltonian is defined by taking all interaction inside the box, the free Hamiltonian, and then the function phi, which is defined here, is really the sum of all interaction which contain 0. And you divide by d squared because here all x has size d squared and there is a multiplicity. Okay, that's so we are discussing the same object, but I prefer the more dynamical approach. Now again, I want to discuss Gibbs measures, but actually we use the definition of equilibrium measures. So what is an equilibrium measure? It's a shift invariant probability measures which satisfies the variational principle, which means you take the free energy, which is the integral of phi minus the temperature times the entropy of a measure, and you minimize over all invariant probability measures. That's the free energy at temperature beta. So we are discussing really invariant, shift invariant measures. So the Kolmogorov entropy is defined as usual. So now there is a remark, because we are discussing about a very simple interaction, phi is Lipschitz. So there is, and for the full shift, there is an equivalence between shift invariant Gibbs measures and the Gibbs measure defined by a DLR procedure. So here, equilibrium measures and DLR are the same, but we will use precisely in the proof the variational principle and with a unique function phi. So that's why my setting is written in this form, although you can rewrite everything in terms of interaction, short range, DLR, on a full lattice. No, I'm sorry, if there are two H, you are right here, but well, usually the entropy of a measure is also called H, so maybe, yes. You mean here? Okay. So okay, you have finite symbols. You have a configuration which is with a single state space. So now P is just the partition of these symbols. One is, let's say you have three symbols, 0, 1, 2. Then you take a big box. Then you take the configuration on a square like this with 0 and 1. And then you have a measure, probability measure. So you compute the minus mu log mu of this finite probability. That's the entropy of a finite probability. And you divide by the volume of a box. You take a limit, the limit exists, and you call this the, let's say, the entropy of the infinite volume invariant measure. So we are discussing, well, what's the usual definition of entropy? Well, okay, so here, maybe you are more familiar with DLR and the notion of Gibbs measure, but it's exactly the same notion here. Okay, so just the definition I will use, G, B, beta of phi is the whole set of equilibrium measures. Well, we have to understand what does it mean that the whole set oscillates. Okay, you know that from Dobrushin, this set has a single point for large temperature, so for small beta. So let's say for the Ising model, for small beta, the cardinality is 1. You have only one Gibbs measures. But for large beta, the set of Gibbs measures is exactly a simplex of dimension 1. So what does it mean to converge here? I mean, here, when beta goes to, for the Ising model, when beta goes to infinity, it goes to the mu plus, mu minus, which are the set periodic configuration, +1 everywhere, -1 everywhere. So there is no chaotic convergence here. We don't say it's chaotic. The whole set goes to just one set. Chaoticity means that the whole set oscillates between two disjoint, let's say, set of measures with disjoint support. So that's just to clarify the notion of chaoticity. Okay, the whole question we are interested in is what are the limits of the whole set. Okay, so let's recall the free energy here. So now I want to at least detect what are the possible measures you get when you take accumulation point of the Gibbs measure when the temperature goes to 0. Well, you define the minimum of the free energy over all shift invariant probability measures. Okay, let's call it the ground energy level. Now, what is a minimizing measure? It's so you minimize this expression. You minimize this expression, I'm sorry, there's no entropy anymore. And you say mu is a minimizing measure if it minimizes this, the integral of it. So it minimizes the energy, let's say the energy at the site 0, the contribution at the site 0. You call this a minimizing measure. And it's obvious, but this is the starting point of a discussion, is that first of all, the free energy converges to the ground energy level. That's very simple. I mean, beta goes to infinity, you divide, it goes to 0. So you get just this part. And also from this inequality, you get that any accumulation point is a minimizing measure. So if you want to find the limit of these accumulation point, you have to understand first the set of minimizing measure. No. Phi is fixed. You fix the energy like in the Ising model. Sigma I plus 1, phi is fixed. It's short range. At the end, it will be short range. So you just fix phi. Now, minimizing means with respect to a phi, which is fixed. Yes?
Short range. They are formed by some compatibility conditions. The vertices have to be like this and that. They have a zero temperature end.
They have zero temperature?
End.
Entropy. You mean the minimizing measure has entropy? Yes.
But they are here considering that at zero temperature the entropy disappears.
Yes, it disappears. But at the end, you have entropy. No. At the end, you have entropy. I will show you an example because I have.
And infinity should be that minus zero temperature.
No. At the end, there is no entropy. And this is the last line. Oops, sorry.
Alright, principle you divide by beta. When you go to beta C, the entropy is finite in Q. I mean, there is no contradiction between you are saying that the result. I think that you think that it's strange because in the end you have positive entropy, right?
Yeah.
But yes.
If you use since you have finite number of singles, the entropy is bounded, right?
Not in the 6-letter model. 6-letter model, you have entropy. It's the number of confirmation grows with the volume, and then you have zero temperature. That's why it's another water.
No, but the entropy here is relative to the volume. I mean, it's
I mean, by this
no.
You just divide from you
Yes. No.
divide by beta.
Well, I will come back to this problem in 1D. No, but the last line is also important because, okay, all measures will go to minimizing measures. So it's very simple. This is the equation. It's a linear equation. So there are a lot of minimizing measures. But actually, the limits. Well, it does not participate at the limit of the variational approach. But the limit, any accumulation point, select a minimizing measure which has maximal entropy among all minimizing measures.
Because it remembers the entropy as it approaches the limit.
Well, all the question is about, yes, how to follow, how to understand the entropy. It's true, so I will explain this. Okay. But the entropy appears at the end because you select minimizing measure with maximal entropy among all these measures satisfying this equation 4. Well, I will give you the result in dimension 1 because it's very easy. It's not really an exercise, but it's easy to understand the result. Well, first of all, so we have to understand the set of the minimizing measure. So there is one case which is very simple, is that the level set, the zero level set, the minimal level set of phi is already shift invariant. Then, of course, any Gibbs measure will converge as a subsequence to a minimizing measure supported on this level set because it's invariant. Okay. Now, but is it true that any minimizing measure is a limit of a Gibbs measure? No, this is completely false. Okay. So you select a minimizing measure. Okay. Now, if there is a unique minimizing measure in X, of course, you converge this totally. But this is obvious. But the problem is that in general, let's say 0 will be the ground level energy. So the level set is not invariant. So there will be a problem to first to understand the set of minimizing measure. So the set of minimizing measure is just the union of the support of all minimizing measure. And the problem is, okay, how to detect, how to understand this set. Okay, so now we will be working on two things. First, we will assume that phi has finite range. I will say exactly what does it mean. Okay, we'll say locally finite. And also, we will have to understand this set of possible limits, so the set of minimizing measure. And we will assume, and this is the main word of this discussion, is we will assume that K is computable. So what does it mean, computable? Or in other words, is effectively closed subshift. So let's define properly the things. The function phi is locally finite, which means depends only on a finite set of coordinates. Or there exists D, and if you take two configurations X and Y, they are identical on this set, then phi are identical. Yes, yes. So X is a big configuration, infinite configuration. And then you look at a window, which is a square of indices. So you look at the states, the value of X on this window. So it's so the alphabet is finite. So it's just a finite number of observation. If you see on this window for two large configurations on a small window, they are equal. Then phi are the same. Phi depends only on, let's say, on this. On the configuration restricted to this table, and phi, they coincide everywhere now. Now, what is a subshift? Subshift means closed invariant, shift invariant, and everything will be shift invariant on the full shift. And any subshift is always defined by forbidden pattern. So that's the word which is important here. Forbidden patterns means what? It's a set of word. You can say word in dimension 1, but in dimension 2, you don't say word, you say pattern. Okay. So it's a set of finite, let's say, words pattern, such that they never appear on the configuration. So you say it's forbidden. You never see it on the configuration. Yes. What does it mean? This means that I take indices 1n to a square, let's say. And then I look at, okay. I look at the square, and on this square, I have some indices. And this is X restricted to the square. And this is a notation to say that this is the whole set of such observation on a square. So I observe a configuration on a specific part of a space, and I call this a pattern. And then I say that an infinite configuration, will be infinite. I never see a sub-word, a sub-pattern of this form in X. I never see this subpattern when I shift everywhere on the whole set, on the whole configuration. But yes. No, there is no condition. It's just a way to define a closed invariant set. Yes, the notion of completion, I will discuss this because it's very important, you are right. But all patterns are finite. Huh? You don't check a condition which is infinite. Huh? Well, so, okay. Okay, maybe you have never seen a Turing machine. Well, a Turing machine is like a computer. You have an alphabet. You have an extra symbol because you want to write words with blank space outside. And you have a machine with states, Q. You start at some initial state. You may stop at some final state. You say that your program stopped at the state Q. And then you have a transition map, which can be written as read in this picture. So what do you see? You have an infinite ribbon where you put your words. Q, the reading head of your machine reads B. Your machine is at the state Q. So what you do is you change B to B prime. You rewrite on the ribbon the new letter. Instead of B, you write B prime. Then your machines change the state to Q prime. But you have two possibilities on the ribbon. Either you read the next character on the left or the next character on the right. That's what you just do. This is your transition matrix. So let's do an example because maybe it's an interesting. Is that I want to do the odometer means I add 1, plus 1, plus 1, plus 1 on the 0, 1 digit. And this, I can do this by a Turing machine. So this is a finite automaton. This is the initial state where I start. And this is the bottom, is where I put the first, let's say, word I want to read. The first word is 0. I want to read 0. I want to add 1, 1, 1, 1. And this, using this finite set of rules, so remember, I have a finite set of rules, I can compute all, let's say, all integers. Okay. So the vertical line is the time, and this is the way you read numbers from left to right. Okay. So let's say, just to say one thing, you start at 0. What you do, if this is the expression you read, 0 change to 1, so 0 change to 1. The two symbols on each side does not change, and you put plus means that the head, which is green, now becomes blue. Now you are on blue, you see the symbol sharp, you change sharp to sharp, sharp to sharp, but then you see the states becomes red and goes to the left, you goes to the left, and so on. So now, you see, if you look at the yellow lines, it's where you see all the numbers, 0, 1, 0, 1, 1, 1, 0, 0, 1. So you compute all numbers. So you see, a Turing machine does, let's say, any program you want. But actually, a more interesting remark is that a Turing machine actually can be seen as a tiling, as a special tiling. A Wang tiling means with squares and colors on the boundary of the squares, and special rules which says that two squares are allowable if you have the same color on each edge. And this can be done. It's longer. To get 001, you need maybe 3 times or 4 times the height of this. So you can do this. But the remark is that, so a Turing machine is a Wang tiling, and a Wang tiling, although it's defined by a finite set of constraints, can enable you to compute many things, can do any program. So when you see a tiling, which means on the space, here you see a tiling, you see implicitly the complexity of any algorithm. That's, I think, one of the most important ideas which is not from us, which comes from, let's say, not really computability. Well, also I want to say, I don't want to do computability. I want to do analysis, but I want to use computability to understand analysis. That's different. Well, the conclusion, so before we start the next, the second chapter, well, okay, we want to understand a system which is chaotic at 0 temperature. So, so do there exist a subsequence? Do there exist two disjoint sets so that if I take the whole set of these measures, the support goes to K0 for odd, for even integers, and for odd integers, for this subsequence, they go to K1. Okay. Now, we want phi as simple as possible. So phi will be short range, the indicator of a cylinder. What does it mean? Phi has 0, 1 value. 0 means the word is allowed. 1 means it's forbidden. So we just check on a window, on a square window, on the whole space, on the blackboard, and this window will be shifted everywhere, but we check. If on this window, so on this, we see a forbidden word, we say 1. 1 means a high energy. If we see a load word, we say 0. 0 will be the ground level energy. We want a shift invariant space given by this exclusion rule, which is a finite set of exclusion rule, which is not obvious that this set may be empty or not empty. If I start with a finite set of rules, I start, let's say, with a finite tiling, and I want to extend this tiling to the whole space, it's undecidable to do this. There is no Turing machine which says just that X is non-empty. Well, if X is non-empty, then of course my energy is 0, 1, so the ground level energy is 0, and the support of all possible limits, or all minimizing measures, are in X, so we want to find K0 and K1.
It may not have shift invariant configuration, or even periodic, it could be quasi-periodic.
No, sure. It's, the whole set is invariant, but periodic, no, maybe, actually, we don't know if there are periodic... yes, the measure will be supported on maybe, yes, everywhere. No, it's, we don't know, actually, well, I will state a new result that has appeared in this year, that, yes, you may choose K0 and K1 periodic. You may choose in advance what you want to check. Well, but for us, certainly, the measure is supported everywhere. Yes, for us, certainly. Except that everywhere, but on two disjoint sets. Well, so we want to do this in dimension 2 because Chazot-Horman did this in dimension 3. So it's an extension of Chazot-Horman. Okay, now, okay, result in dimension 1 because it's easy. And maybe I answer your question about entropy. So again, I want to take short range. So here I just use a potential which depends on two neighbors. Let's say x0 and x1. I like to work also in, let's say, Frankel control problem. So it's exactly this kind of problem. But the state is finite here. So I use the transfer method in dimension 1, of course. You introduce a matrix, ij. Ij is just one of its symbol, 1 to n. And you introduce the Boltzmann factor. Now you have a matrix, positive, use Perron-Frobenius, use the largest eigenvalue, the left and right eigenvalue, you normalize, and then you have an explicit formula for the Gibbs measure. It's unique in d equals 1, and this formula is given by the total energy of a box where you fix exactly the value of what you see on a box of length n. You see a configuration which is exactly I0 at 0, I1 at the index n. Okay, you normalize, and here the partition function is more or less given by the power of this largest eigenvalue. Okay, you have some kind of cocycle here from the beginning and the end, which gives you, at the end, an invariant measure which minimizes the free energy. It's the unique one. Okay, so let's recall the ground level energy, which is the minimum of all mean energy among all shift invariant probability. Actually, there is another way to find this ground level energy. You take a finite box, and this is true in any dimension. You sum the total energy, you minimize over all configuration, and you take the limit, you divide here by the volume, it's n, and then you get the ground level energy. Okay. Now, you want to say, what is the set of minimizing measure? So here it's explicit, and the next transparency will give you an example to understand this. But you have this defined forbidden transition from I to J. What is forbidden? Forbidden means that there exists a periodic configuration which starts from I, or cycle, and goes to J for the next step, and then returns to x0. It's a cycle, and on this periodic configuration, the energy is strictly larger. So that's forbidden. If any edge on your graph belongs to a cycle which has large energy, then it's a forbidden edge. Now, the set of support of all minimizing measure is exactly the subshift of finite type given by the non-forbidden transition. So by the transition ij's, which are included in a periodic way, in a periodic cycle where you have equality here. Okay. So now let's go to an example here. So I give you 4 symbols, and you look at all infinite configuration with 1, 2, 3, 4, and okay, here I have no edge from 1 to 3, so this is not allowed to jump. So you could put a very high energy also if you prefer. And here the notation is, if I go from 1 to 2, then I put -1. You see the arrow here, -1. If I go from 2 to 2, which means that in the large configuration, I see 2, 2, and then I compute the energy of this box, 2, 2. The energy of this box is 0. Okay, here it's 0. Now, I do this for all energies. So you may say, what is the energy from 1 to 3? It's very high. Okay, it's 1000. Okay, it will change a little bit the computation, analytic computation, but here I could say it's infinite. Okay, that's what I say. Okay, now the question is, take the unique Gibbs measure here, take beta goes to infinity, and look at where it goes. It goes actually to a unique one here. The mean is unique here. So why, and where it is, you see, you have to compute all cycles. Let's say cycle of order 1, let's say, of length 1. 0. The mean energy is 0. Cycle of order 2. The mean energy is 2 plus 0 divided by 2. The length of the cycle is 2. The mean energy of this cycle is -1 plus 0 plus 1 plus 0. It's 0 divided by 4 is 0. Actually, you compute all minimum of all cycles, you get 0. And you just keep, you just keep all minimizing cycle, and you get a graph. And if this graph is connected, you have a unique measure, and the Gibbs measure converges to the measure of maximal entropy of this subshift. So you have a lot of measures here. Let's say the periodic measure here, 2, 2, 2, 2, 2, 2, the configuration, but actually it selects the one which has maximal entropy, and there is a unique one. So that's the convergence. Well, that's so yes. Usually, you get measures with maximal entropy when it's not periodic. Yes, I think generically, in the sense that if you put faces here, if you put numbers, generically you get periodic measure. Okay, if you put here for the Begg measure, you put the numbers here, and you choose randomly with respect to the Begg measure in R, let's say. Now, generically, let's say, except for a set of phases which are included in hyperplane, union of finite hyperplane, except on this set, everything will go to a unique measure, of course, but which is ergodic and concentrated on one periodic orbit. So you choose a periodic orbit. So this is for the generic picture. Well, here, the other picture here is more or less the same. I define a minimizing cycle, but here I see two disjoint things, and the problem is the Gibbs measure, where does it go? does it go to, so you see all this system has the same entropy, maximal entropy, topological entropy. So does it go to the top or the bottom? But actually there is a symmetry. So hopefully you don't have to do anything. You permute 1, 2, and 4, 3, it's a symmetry. So at the limit, the measure is also symmetric. So it's 1/2, 1/2 of the two maximal entropy measures of these two shifts. Well, but it's not easy actually to prove, and this is a theorem, that actually for short range, locally finite potential, the limit always exists without taking any subsequence. Of course, the limit is minimizing and possibly non-ergodic, but generically it will be just a periodic orbit. And it satisfies, it has maximal entropy over all minimizing measures. And you have also, let's say, algebraic estimates. So it's a barycenter of a minimizing measure of maximal entropy on disjoint subshift of finite type, like the example as before, and the coefficient of a barycenter are algebraic numbers. You can prove this. So Raymond proved this. So now, there are two possibilities to extend this. Either your function phi is very complicated, is not locally finite, or the set of minimizing measures is also very complicated, has a lot of complexity. So Charlotte Horman did this in dimension 1, so we are in dimension 1. You take an invariant compact set with some kind of complexity, and you take the simple function, which is the distance to this set. So of course, on this set, which is invariant, phi is 0, outside phi is not 0, so the ground level is 0. So anything should converge to a measure, minimizing measure, supported on k. So they are able to find such a k where the system is chaotic at 0 temperature. So the unique Gibbs measure actually oscillates between two measures supporting on k, two different measures. Well, you can do the opposite, and it's what we did with Rodrigo. And here we want a more complex phi, not the distance, but at the limit we want the configuration 0, 0, 0, or the configuration 1, 1, 1, 1, 1. And we can also prove chaoticity where you oscillate between these two configurations at the limit. What is interesting here is that actually it's a family of function, a family of phi, and we are able to do a phase diagram and try to, although we have not completely understood, but define some kind of energy barrier, because you have, let's say, two whales, one which is around the periodic configuration 0, another one which is around the periodic configuration 1. And these two whales, you look at the boundary, and the question is how to go from the energy point of view from one periodic point to the other one. And if the barrier is positive, you always converge. If the barrier is 0 on both sides, from 0 to 1, 1 to 0, then there is a possibility to find a phi which is chaotic at 0 temperature. Of course, you cannot exclude symmetries. So if there is some symmetry and this relation is also true, then there is no chaoticity. So now it's what we want to discuss, this extension in dimension 2. So it's what we have done with Sébastien Barbieri, Rodrigo, and Grigorio Dalevedov. So they exist, contrary to what you may think, there exists a locally finite potential in 2 dimensions that is chaotic at 0 temperature. So in 1 dimension, it's non-chaotic, in 2 dimensions, it's chaotic. Finite, locally finite means there is a finite set of rules. You can think in terms of tilings, and you have with a finite set of rules, and when you freeze your system oscillates in terms of the whole set of Gibbs measures between 2 different subsets of measures. Well, this has been done in dimension 3. So we tried to reprove this theorem in dimension 2. So their proof does not work in dimension 2. And Charlotte Shinoda also simultaneously did the same result in dimension 2. But they published this at the same time as the thesis, but their proof is different. And there is a recent result that I have not really read, so that would be interesting, is that you can fix in advance the set of limit measures you want to obtain. And let's say if you have a finite samplet of periodic measures, then it's chaotic in the sense that the diameter of a set of Gibbs measures goes to 0 for some subsequence, and along this subsequence, and any mu is accumulation point of this subsequence. Well, I will not discuss this. Now, I want to say the general strategy of how you prove this and why computability is the important notion. So the problem is at the end to define a set of forbidden patterns, a finite set. And we want, and our final potential energy will be, if you see a forbidden word, the transition is not allowed, so you have a high energy. 1, if the transition is allowed, the energy is 0. Okay. You want to make sure that the shift, the subshift associated with this set of forbidden words is not empty. And you want to find a cooling sequence, beta k goes to infinity. You want to find any Gibbs measure. So just recall what is a Gibbs measure. So it's a measure which, yes, here I have written the pressure, I'm sorry, not the free energy, so which maximize the pressure. So mu beta k maximize h mu minus beta phi d mu over all invariant measure. And we want to show that along this special subsequence, on odd integers you go to mu1, even integers you go to mu2, they are different. And the support, of course, has to be included where phi is 0 is the ground level energy. Okay. So the problem is we want to find this in dimension 2. But the main idea, which actually also comes from Charlotte-Hochmann, is to start with a set in dimension 1. So we are going to start with a subshift in dimension 1 and extend progressively to a subshift in dimension 2. In dimension 1, this subshift will have large complexity, not locally finite, not finite. It will not be a subshift of finite type. But at the end, after the extension from 1 to 2, it will be of finite type. Okay, so the alphabet here is 0, 1, 2. 0 is a marker here, and we want to select 2 subalphabets because we want to say that the Gibbs measures, let's say, for some temperature will be associated to symbol 0, 1. So all sequences with 0, 1, and the other Gibbs measure will be associated to all sequences 0, 2. So that's why they will oscillate between 0 and 1, 0, 1, 0, 2. So 1 will never appear at the end in the limit here, and 2 will never appear in the limit here. Okay. So we construct inductively languages. So we have to say what are the forbidden words. So here I prefer to say what are the allowed words, what is allowed. So actually the language is made with 2 words. We have only 2 words. So with some special LK some length. So we have a scale, and it's very important to detect some scale where you want to define your objects. So some scale some Gibbs measure will use a scale located, or let's say a subshift located with symbols in A1, and at the next scale, the Gibbs measure will select measures, let's say, will give more mass to measures with these symbols. Okay, so here I will say exactly what is the next word. So each time the language has 2 words, 1 word with 1, 1, 1, 1. So I put a lot of 1 and AK, and here I put a lot of 2 and AK. Okay. Now this will give us a finite set of constraints, and we just concatenate everything like this. So we can concatenate a word 1, a word A, 1A, 1A, or 2, 2, 2, 1A, and A2, A1. So we concatenate this, and this gives you a subshift of finite type at scale K. So we have, of course, at scale K, a subshift where you just concatenate these words. So you have 1, 1, 1, A, 1, 1, A, 1, things like this. This is a
AK can be 1, yeah, it can be 0 or 2 or
yes, okay. Yes, AK1 will contain only symbol 0, 1. I will give you a definition. AK2 contains only 0, 2. So here at the end, I have two subshifts, just with symbol 0, 1, just with symbol 0, 2. So I want to oscillate between two subshifts, 0, 1, 0, 2, 0, 1, 0, 2. And 0 will be the marker, will decide at which shift I go. Okay, so I take the whole set of constraints. Now it's a union, so it's countable. And I define the subshift associated to this constraint. Well, everything will be done in an algorithm, so it's computable. That's a magic word, it's computable. So let's say what is important here. What is important is that I want, so I have two subshifts. At each scale, I have two subshifts of finite type. So one is contained with symbol 0, 1, and for 2 is contained with symbol 0, 2. And what is important, and I have a sequence of scales, and for k even, k equals 2, then 2 dominates in terms of the entropy. So remember, the idea we use is that a Gibbs measure choose when the temperature goes to 0, it chooses a measure of maximal entropy. So it will try to choose the measures with maximal entropy. So inside the shift, I have two subshifts of finite type. One has large entropy. So for k even, the mu beta will go to something which is included with symbol 0, 2, and vice versa for k equals even, for k is even. So now let's see how you alternate the complexity. So you start, let's say, with 0, 1 for at scale 0, 0, 2 at scale 0, for 2 and 1. Now, suppose AK is defined. You want to define k plus 1. So k is even, k plus 1 is odd, and for odd, you want large complexity for 1. Large complexity means you just repeat the word, AK, 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 it's a repeat. It's not IID, just repeat the word. Here, you want a small entropy. So what you do? Well, you start with the initial AK2, you end with the initial, and in the middle, you just put 2, 2, 2, 2, 2, 2, 2, 2. You may say, okay, why the entropy is really alternating? It's because here, at least you have 0 in AK each time. So you see many times 0, 0, 0, 0 here. So that's why you need a marker. But here, because you put a lot of 2, you say 0 here, and just at the end and the beginning. So the frequency of 0 is small, the frequency of 0 is very large. So really, the entropy here is extremely large. So k is even, k plus 1 is odd. We are on this slide, the entropy of the shift with symbol 0, 1 is very large. Okay, so that's a way. So there are many ways to do this, and it's just a choice. So that's not unique. Well, here I have explained I will go faster now. So the entropy is not the right notion actually. So it's better to define the frequency of 0. And I will explain why the entropy is not important, because as soon as you extend a subshift in 1D to a subshift in 2D, you lose the entropy. The entropy immediately goes to 0. So, but the complexity, you keep the complexity. So I want to keep the complexity, which is the number of 0 here, the number of 0 here. And I repeat the last slide in terms of complexity and not in terms of entropy. Okay, so now what you do is constructive. So you have an algorithm, you say what is NK, and so on. But be careful. You see, when you say, I put a lot of NK, usually in a proof, you say, okay, I put a lot of NK, it goes to infinity, I have. But this is not recursive. You say it goes to infinity, it's not recursive. Recursive means NK plus 1 is given as a function of NK, let's say NK to the power NK. So this is recursive. Of course, usually in an algorithm, in a proof, you never say a specific form of all your parameters. But you could, and okay, you define properly what is NK. You have to do this, otherwise, if the set you define of forbidden world is not recursive. Okay, it's recursive, so it's given by a Turing machine. Okay, so now that's the next step. You embed a one shift in a two shift. How do you do this? You just extend vertically. Okay, I did this here. The 1D, you see 1, 0, 0, 0, 1, and you want to say it's a 2D subshift. Invariant, you just extend vertically by 1, 1, 0, 0, 0. It's obvious. But you see, that's the remark. As soon as you do this, if the 1D has positive entropy, the 2D has 0 entropy, so you lose the entropy. So that's not very good. Okay? Yeah? Now, you want to say, and this is the main result that we are using, so this is maybe the main slides, which is not us, it's from Aubry-Sablick, but you want to say that you start with a computable set of forbidden words. You extend vertically, you call it X tilde. All the zeros are vertical, are the same. Then X tilde is sophic. What does it mean to be sophic? Sophic means that it's the projection of a subshift of finite type. So what does it mean? Let's say in this picture, just I did that is why I put some colors. When you extend by 1 and 0 vertically, you can put colors and rules so that when you fix the rules, you see, you have a finite set of rules which says that if you try to find all the configuration with rules with 0 and 1 randomly chosen, but with a finite set of rules, then actually you forget the colors, you see exactly 1, 1, 1, 1, 0, 0, 0, 0. Okay. That's not obvious. That's Aubry-Sablick. So there is an extension, a commuting diagram. The projection is surjective, and it's defined by a one-block factor map, which means that you erase the color. Here are the original symbols, 0, 1, 2. You put colors, you erase the color, and you get after you erase the color, you get the vertically aligned subshift. So we use this to get a finite set. It's sophic. You get a finite set f hat of forbidden words. Okay. Now the last step, because you don't get entropy, and at the end the main proof is about entropy. So you want to choose each time a subset with large entropy, and you want to oscillate. So to get entropy, you just duplicate 0. If you see 0, you put randomly 0 prime, 0 double prime, and so on. So at this time, the entropy becomes log 2 because you duplicate times the frequency. So that's why you can recover, again by a finite set of rules, a set which has positive entropy. And since the main construction is to oscillate the frequency of zeros, the frequency of zeros in the subshift 1 will be very small, or at the next level will be very large. You oscillate, and the entropy will oscillate. So that's the end for the construction and for the proof. I will not do too much. But so what is our contribution for this? Because we are extending Chazot-Horman. The contribution is that we recognize two estimates that were not explicitly written in their proof. And the first estimate is about a shift reconstruction function. So that's an interesting object. You start, and I think I answer one of your question of reconstruction. You start with a set of forbidden patterns, and you define two notions. So be careful; they are almost the same. So be careful. You take a finite pattern, like on the blackboard here. You take a finite pattern, and you say it's locally admissible if no forbidden pattern appears in this pattern P. Okay. And then you say it's globally admissible. That's very different. If actually it's a sub-pattern of an infinite configuration. So the question is, if I give you a pattern like this on the blackboard and a set of rules, can you extend to the whole set? So that's locally, globally. That's a big. But there is a reconstruction function. Given n, you want to extend a small pattern in P. Well, you have to enlarge a little bit the box and say, if the box is locally finite, the blue square says that you check everywhere the local condition. If it's locally finite on the big box, then actually the small box can be extended to an infinite configuration. This always exists. But the problem is that, is it computable? No, you have many ways to extend. It's not computable. But I have to start with a computable set of forbidden words. So I have to say that everything has to be chosen so that this is true. So that's maybe where we disagree with Chazot, Hoffman. This is not computable. Well, okay, they have a way to say something, but okay. Now, well, the lemma we have to prove. So in addition to what is not in Chazot-Hoffman is that you start with f tilde. Well, f tilde is simple, so you can the reconstruction function of f tilde is big O of n. So, and then you show that now the reconstruction function of the Aubrey-Sablik extension, well, has some growth, exponential growth. We don't say that the growth is a computable function. We just say it's finite. So we never use how to see how the growth, what is the growth. Well, and we prove that our set, well, satisfies this. Now the next thing we think it is missing in the proof of Chazot-Hoffman is the notion of complexity, relative complexity. This is a very basic notion. You have an extension from x hat to x. You look at a pattern, which is globally admissible P on the basis, and you look at all patterns on the top, which project on the basis, and you compute the number, the cardinality of these extensions. And you take the sup on P. This is the relative complexity. And you prove that the relative complexity, and because you divide by n, goes to 0. So be careful, it's not by n squared, which should be the entropy. So the relative entropy is 0. The extension has 0 entropy, but we want a little bit more. So we have to divide this, and this is clearly missing in their proof. And hopefully Chazot-Shinoda recognize also that this is important. Okay, so now final remarks, and this will be the end. I think I did not. I had. Okay, no, but it's just 1 minute. Okay, so we use Aubrey-Sablik as a black box. Well, we can say we don't really understand why generally some tiling exhibit a chaotic convergence. We don't understand. We just use some extension. So how to recognize that a 2D tiling with a fine set of rules contains a hidden 1D subsystem that is chaotic, that is complex. Well, all the quantities, this is an important remark, are computable. But computable means that there is an algorithm with index by integers. So we have only a countable number of algorithms. So at the end, we have only a countable number of functions, of potentials, of sequences, of everything. So what about if I take another sequences of temperature, which is not computable? Okay, they exist because the set of sequences has the power of R. So you have many subsequences of non-computable temperatures. What can we say about the convergence? We cannot say anything. Okay. Now, the Aubrey-Sablik extension is too large in the sense that the number of corals you have to add is extremely large. Imagine this odometer, which is an algorithm, and you want to write this in assembler language, and then this is just to add 1. And imagine an algorithm, so you get maybe giga of symbols in the alphabet. So there is no experiment to do to understand this. So that's not very good. We don't say anything for non-invariant Gibbs measures also. Everything has to be invariant. So in d equals 3, we don't say anything for the Gibbs measures which are not invariant. And I guess that for quantum system, this should be interesting also. Though the first thing to define is really the set of minimizing measure. The limit also it's interesting to understand the limit when the temperature goes to 0, but I think for us it's also interesting to recognize first the possible set of measures which could be a limit. The set of minimizing measures, I think it's not so easy to define for quantum system. So I think, thank you, that's the bibliography we have used, our paper, the Chazot-Horman, Shinoda, and a very recent paper by Giral, Saplik, Tahati. Okay, thank you.
So when you take Penrose time,
What?
Penrose
Penrose tiling, yes. Well, Penrose tiling, yes, does it fit here? Well, it would be interesting to understand this, yes, the Gibbs measures of this. So for one tile, which are square with edges, and you say that two edges have the same color, this is easy. It's like a lattice system. And I don't know if the Penrose tiling is, let's say, some kind equivalent to one tile. This is not clear. So yes, that would be an extra problem, yes.
That there is a old paper by Heisenberg, I don't know if Heisenberg is Simon or Heisenberg, on the variation of approach for ground states.
It's old,
It's very old.
Okay.
It's kind of a canonical. It's likely in the appendix on our paper.
Okay.
So just look, I think it's what you're saying. Radiation approach, and then using only the energy, but then you use the entropy.
Okay.
In your paper with Van Enter, Sokal, okay. Okay. Mm-hmm.
Does it make sense to analyze the problem like you're doing at finite temperature?
Yes, certainly.
No, this is what Philippe didn't quote, but there is another paper of here, but even L'Italian and Daniel Coronel wrote a paper exactly because I think it also Thiago and Violeta, they wrote in the first paper that maybe we can try to see this as some kind of critical temperature positive, right? That's what.
Mm-hmm.
So it was open problem with the amount of time.
And of course, you can go from the left and one from the right.
Yeah, I mean, you should. Is it easy if you came from the side where you have one, right?
Yes.
Otherwise, you are very big, you're just getting in. But if it is possible to have only one, so you have to do this, right? And okay, Arnaud wrote this with Violeta, and I think in the physical system there is nothing. And there is one paper looking at once, I guess, from Université and Daniel, they are from Chile, right? And they use thermodynamic formalism for complex dynamics. And what they told me, I didn't read the paper, that they are able to construct so the potential is the geometrical potential, it's log of the modulus of the derivative of something or some function. And they do the thermodynamic formula for this family, and they have an example where you have positive temperature and the given measure of space.
From the right?
Yeah, from the yes,
The school means that.
No, you are increasing.
No.
You're heating, right? But there is, I think that there is no physical meaning. They told me that this came from the holomorphic part. Something they had some properties of this potential. But that's why I think that there is nothing for this.
I think Renaud is working on the trees also. Renaud, le plaider, he's working on trees. I think he's working on positive temperature, yes. The same problem.
They have
They are working.
okay,
I know.
more questions. So thanks. Thanks. Now. speak about the analysis of information, new conformity, the demand, the phase.
Okay, thank you very much, Rodrigo. Thanks for this opportunity. It's my alma mater is here, USP. So it's when I arrived here, actually I arrived in the last day of the last month. So I visited my family, and now I'm visiting my academic family. And okay, this is a result of I mean, a few days ago. We mentioned about what all this started about the drinks, the caipirinhas, and then after that, one of the first babies of this this big project was this paper, and this also is the paper. Oh, yeah, yeah. So. This is the thing. It's this paper had some versions, so it's like when you make too much recipes for a cake. So now there's a lot of cakes to share, and actually this will be a challenge for me because it's the first time presenting for a very mixed audience between classical and quantum. So there are results including both sides of the theory, and okay, so. Let's get started talking about Markov shift spaces. And very briefly, Markov shift spaces, when I have for our case, it will be a counted alphabet and a matrix that allows the subsequent states. If it's 1, it's allowed. If it's 0, it's not allowed. And Markov shift is the shift of is the space of the sequence of infinite sequence such that the matrix is allowed consecutive states. And also the dynamics in this space is the shift map. It's basically cut in the first coordinate. And a little bit about the topology of this space. It's generated by this cylinder set. So you fix a word. So the first element that coincides with this word would be the cylinder set. And we say it's admissible when the cylinders are not empty. And basically that means for transitive shifts that this, for this word, every 2 consecutive states they're allowed by the matrix. Okay. So equivalently, you can say this is a subspace topology of the product topology of the full shift. And it's also a zero-dimensional Polish space. And for this topology, the shift map is a local homeomorphism. And these are very, very important examples of the theory. The full shift, basically, you allow every state. And the renewal shift, which basically you have a symbol, a renewal symbol that goes to every state, and then the other states are forced to go back to 1. And some important features about these spaces, especially here, we consider the transitive shifts. That means that 2 symbols can be connected through a word. So AWB is admissible. And topologically mixing sometimes, especially the renew shift and the full shift. So there's a minimal size between, when you fix the 2 symbols, there's a minimal size such that for size length greater than that of the word, you always have a admissible word. Okay, so there's some topological facts about this. The first one actually doesn't need transitivity because it's the consequence of the Thieullen theorem. So when the alphabet is finite, the shift is compact space. But if the matrix is row finite, I mean, every row, there's only a finite number of ones. It will be locally compact, but it's not compact. And if it's not, the shift is not even locally compact. So when you work with this kind of problem, for example, the full shift and the renew shift, they are not even locally compact. You lose very good tools to solve problems in this space concerning probabilities and also the C-star algebra side for the theory. But okay, so before I introduce the system algebra part, I have to mention that in this space we're interested to put a model which is like an energy function, and it's inspired from the thermodynamic, from the statistical physics, but it's a little bit different way, just a real function in space. So this is some of the most common regularity. We have this potential to develop the theory. And for us, I mean, we're interested for this work, most of the results are, they satisfy the Walters condition. So you have this, this Fn is the ergodic sum, the Birkhoff sum. And we impose this to be finite, but and also the limit sup of this Birkhoff sum, the variation of this Birkhoff sum should be 0. But I thought that many of the examples here, they are also, I mean, the concrete examples tell you these are actually summable variations. Okay, so in level of generality, the Walters condition is the regularity, which is a more weaker conditions to develop the thermodynamic formalism. And now, briefly, I'll talk about system algebras and chemistry states. So I am very thankful for all the speakers. The last talk this week, they're defining this for me. So thank you very much. And okay, let's talk about some Kunst-Krieger and Excel-Laka algebras. So, okay, this is a concrete construction. Actually, there's the original version of these algebras. They are universal algebras, actually. But basically, now we consider the L2 of sigma A. So the index here are the elements of the shift. So this is the canonical basis of this shift. And this is a non-separable representation we are going to construct here. So these elements are bounded operators on this space, in this Hilbert space. So basically, Si, you add a symbol if you can, if the matrix allow it. But it's adjoint, you shift the word if the word belongs to the cylinder I. Also have this projections in this space. Basically, they check if the element is inside the cylinder or the shifted cylinder. And this operates the pairwise commutative. But I'll explain more about this later if it's needed. But basically, the representation will be working here. There's actually two representations, this concrete side to show you the operators acting on a very explicit space. So basically, I have the Kunst-Krieger algebra. It's when it happens when you have the finite alphabet, and the Excel-Laka algebra this alphabet it's not finite. In this case, would be countably infinite. So basically, the alphabet is n, and these operators are basically you have a word. For us, it would be admissible, otherwise, it would be 0. Length with this length, and these operators, the juxtaposition of the operators. And the basically, it's a closure of the span of this operators. Basically, an operator like this does this. So let me explain. So the first thing is to shift if the element, let's say, sorry, you have like a word is the elements of the letters here. So if there's a beta here, you cut the beta word, and then you check after you cut it. You check if you can include the symbol I in this for every symbol I it's possible. The matrix allows it, and after that, if it's possible, you glue an alpha word here. So this is how these operators work in terms of the words. And this, for now, I want to define the commutative matrix which we construct. The commutative sister algebra. We're going to construct the generalized space. So these two algebras here, they are commutative, and the generalized Markov shift. So let's explain a little bit about the story of this. This algebra actually started. The story started in '63 when. Sorry, I don't speak French, so I will say Dixmir, but maybe I'm wrong. This is there's this question about the existence of simple infinite sister algebra. And the first concrete example was made by Kuntz in '77, and later this was generalized because this example is the full shift. Later, this was introduced the transition matrix, and then it's a very concrete connection with the shift spaces as an algebra that codifies the relation of the matrices. And later, Kuntz, Pesky, Reburn, and Renault, they extended this notion for the row finite case by using Groupoids sister algebras. And in 1999, Huexel and Marcelo Laca, they did they removed this condition. And finally, in 2000, Renault introduced the Groupoid approach for this generalization. And okay, so now we have this commutative algebra. So this space is basically the spectrum of basically the space of the non-zero star homeomorphisms in this space. So this is the space of the generalized Markov shift. Since this is it's unital if and only if XA is compact, but if it's not, you have a unital version here. Basically, this algebra is the unitization of this algebra. So this space is the one-point compactification of XA. And the good thing is we recovered the topological features that could make this easier to construct the theory. So this space is always locally compact. In many cases, compact, including cases that the Markov shift, the original one, it's not even locally compact. For example, the full shift is compact in this case. The renew shift is compact in this case. And actually, if the matrix has one line of ones, it's a sufficient condition to make this compact. So now a little bit about the groupoid side of this. So I inverted the question about the motivation of the study this thermodynamic formalism. So the idea is, who is XA? So it was known before that for the Kuntz-Krieger algebra, if you exchange this for sigma A, this should be the sister algebra, groupoid sister algebra should be the isomorphic to the Kuntz-Krieger algebra. So basically, this space is the space that make this function about connecting these spaces. So this is why it's called generalized Markov shift space also, and also because this includes the usual one. So, but I'll explain with more details. So this groupoid has less composable parts. It's constructed in terms of being equivalence relation, for example, because in equivalence relation groupoids we have this for probability in general we reproduce the properties, we define the equivalence relation. So this is, when you make the product, you are basically using transitivity, for example. And this is the range of source maps. Basically, you make a 0 here, and you make a 0, but keep it the other side of the triple. One thing that's important, that this is why I told you I inverted the order, because the shift, okay, it's well defined in the sigma A, but this is the difference here, because now you have some words you cannot shift. We call it empty words, but these empty words could be many, for example. Okay. In order to make this more easy to understand, I will give you a geometric view of this. So basically, we consider the Cayley tree generated by the free group of the alphabet. So F here, it's F of n. And we look, if you look at the Cayley tree, you have, like, for example, going to this positive parts by multiplication. So this is, for example, the unit of the group. So we can keep going here, and there's many points actually. So because we have many generators. So if you go in the other side, we multiply by the inverse. So basically, it's like this, and we put a 0, 1, so we put two-state, like a two-state construction on each vertex. So for this talk, if I make a fillet point, basically it's when this when you take the projection here for an element in O1 power F. Basically, this if J is filled, so this is like this is basically the projection here will be filled. So it's 1, and it's not filled when this is 0. Okay, so you label the vertices of elements, the oriented edges as the product of this group, and I'm going to include the sigma A, the standard shift, to the generalized one. So the first thing, I mean, the explanation for this is more technical, so I prefer to just show the rules, and then it's better to understand the space. So basically, we impose that the unit is filled, impose that every subword of the word you pick is filled, and also impose a relation to the past. When I say past, I mean, if you have a vertex here, so the past is the vertices that are arriving here, and it could be also the rest of the tree, of course. But basically, we have a rule to determine in a unique way which vertices in the past they are filled or not, and this is given by the matrix. So basically, the matrix. If you have, for example, a word, a symbol, and you want to test if another symbol is filled or not, you look at the matrix. So this course should be allowed by the matrix. And we make this canonical inclusion by taking this unique configuration. This space, it's not important now. You can only consider this one, because this is more technical. So you just look at the unique configuration that makes this. And the generalized Markov sheet space in this case can be seen as a closure of these configurations in the sigma A with this canonical inclusion. And sometimes you must remove a special point there that corresponds to the compactification point. So basically, it is only filled here, and it's not filled in the rest. Only in the identity of the group. And see, this is now basically we can see these as states in the Cayley tree. So, and also there's you can identify which kind of element there is filled. So basically, because of these rules, when you take the closure, this is only if you have this is a word, admissible word, not a admissible word, but inverted, because now we were in a group, and or the product of them, or separately, or the unit. And there's some interesting relations when you make this inclusion, because actually this preserves the topological properties of the shift, Markov shift. The first one is it's the topological embedding. So the sigma algebra is containing the shift sigma algebra is contained in the generalized one. That means you can extend and restrict the measures whatever you want and be well defined. For example, if you extend it, you can just put 0 in the rest, so you can see as a subset of each other. And actually, this will be more important. I didn't put this result here, but I'll tell you now. Later, we're going to talk about eigenmeasures, about conformal measures, and also this preserves this structure. I mean, every conformal measure that is in the sigma A also is a conformal measure of the bigger space. So this is a very good inclusion, because it preserves not only the measure structure, but the dynamical structure related to the measure theory. And if the shift is locally compact, we recover the original shift. More than that, now we have new elements here, so we must characterize them. And the first thing I can tell you is when this complement is not empty, it's also dense in XA. And how are these elements? So basically, this is a typical element of this space. All the elements are like this way. It's like sometimes it stops in the unit, but it's like a river going only forward. So you won't see something like an chalk. You never see something like this. So you have a word here. You have a product here. You have a product here. You never see this thing. This never happens. It's only a confluation of the edges. So this never happens. But it can stop in some point, or it can keep going forever, like the elements of the standard shift. So we have some special names here. This last word, it's called the stem of the configuration. And basically, when you talk about finite words here, we are referring to this word. And this hair of edges before this last word for these elements, basically these elements that are all finite words, we call it the root. In the original paper of Hui and Marcel, they constructed the space, and actually there's a definition that included more elements there. But for us, we just take this one. So basically, you can have, for example, two words with the same stem, so they basically have the same word, but they are different here. This is the way we make differentiation between two equal configurations. But the way I'm going to present here, it's more, maybe could be more easier, because this actually, there's the notion of a Y family, which will be important through the whole talk, and this basically shows you that a partition that dynamically separate this complement of XA, and this is when we have conformal measures, actually there's a bijection of these elements with the conformal measures, because the extremal ones, I mean a bijection between the extremal ones, because the extremal are precisely the ones who lives here. But I will recall this later. And as I told you, the shift map is, when you see this as an element of sigma A, I mean the standard shift, you can rewrite the shift map, and basically it's like a translation. So, but you must be careful here, because remember that as a main rule here, this always happens. So if you shift it too much, it translates too much. So you cannot get out of the space. So this is this restriction, but actually it's not a big deal actually. But the good thing is this is an open set. So topological properties are preserved again. And now we want to construct, so the idea is you can shift here a finite number of times until you translate it to the past, until this, this picture starts, the last, the stem here becomes E. So it's limited. You can, these words are basically finite words, so you cannot shift it forever them. And okay, so how could you construct these families? So basically, you look the sequence of elements. We see the matrix is a sequence of elements of O1 power n with the product topology. We take the non-zero limits of these points, and we connect we can see these limits as a subset of n, and then this will be the path of an empty configuration. And then you take the pre-images. But, okay, this is a lot of words, right? I'm gonna make an example for you. So let's think about the renew shift, for example. This is the renew shift matrix. So when you take the limit point here, there's only one here, because each of these coordinates disappear. So it's basically this, column vector. And now you're going to construct the empty stem configuration, and then you take the pre-images, and then you have the whole space. So it's basically like this. Okay, so we have this vector as the unique limit point. So this corresponds to the set 1, because it's the only one who is 1. And now you start to create the empty stem configuration. So basically the unit, so 1 is the only one, so this should be 1. And then we use the rule of the matrix. Remember this, when you can check, then this happens if and only if Aij is 1. And this is what we have. For example, this is a construction, basically this picture. So now we're going to apply this matrix rule. So in order to arrive in 1, there's only two options, 1 and 2. So we make it. Now we have evaluated on each of these vertices. So again, on 1 and 2 here, and now it's 1 and 3 here. So we keep going, and then you keep going, and then you keep going. Doing this forever, you have the empty stem configuration. So this is the, for this case, since there's only one limit, this is the only one empty stem configuration, so there's no ambiguity between different configurations of YA. And now you can construct the remaining ones, because you can translate to the future, like take the pre-images. So since this is the only one YA family, because only one limit, you can just look like this. So, okay, when you go push this to the future of the configuration, there's only one option. So this is translated to the future. So this should be 1 now, and this is the unit of the group. Now, if you take again, you have two possibilities here. You can go through 1 or 2. And then when you go through 1, you have this path, so this is the identity. And when you go to the other side, you have this identity. So you can keep going, do this, and then you can reconstruct everything. And in this case, as you can see, in the renew shift, the words all the time ends with 1. There's a reason for that, because the only possible way to construct the finite words must end in an infinite meter of the matrix. Okay. So these families, they have good properties. First, because they make like they are a partition of YA, and also they have invariance about the shift. So if you only consider the intersection with the domain of the shift, this is YA family. If you shift it, you recover the family. So they're dynamically isolated each other. And this is why actually one of the main argument that's just to show that this the extremal elements, I mean, if there's extremal element living in YA given mass 0 for the complement, so this grants us that this extremal measure for at least one side of the proof that this should be the extremal measure should live in this set and give 0 to the rest. Okay, and also they preserve the past. Let me show you again. Because you translate into the future these configurations, the root is always the same. See, never changes. So inside of the family, the root is the same. So the way to differentiate two configurations, you look to the stem and look to the root. If the stem and the root are the same, they are in the same family. But you know, if there are two configurations that are equal, the difference would be in the root of the configuration. And this is we call this stem uniqueness. Inside the family, there's only one configuration representing a word. Okay, so this is, for example, an example of the renew shift. We shifted like 3 times, so this is a copy of the empty stem configuration. So basically, it's ramified the same way, and this is correspond to the word 3, 2, 1 in this space. And this is how the shift map acts. So basically, translate, you make it like the sorry. So you remove by the left the configuration here, and then so you push back to the past. So see, this I can only do 3 times. Okay, so now let's talk about generalized thermodynamic formalist, and now talk about the results. So how much time do I have? Yes. So I'll be able to tell everything. So my experiment worked. So okay. So in order to start this first I want to emphasize that the shift is not defining the whole space, but also the potentials are not. The reason for this is in the standard Markov shift space, I mean sigma A, the theory is developed for unbounded potential. So we want to keep this. So since we already have problems to define this shift map in this space, sometimes you can, but since there's no reason for this formalism for this work, but Keisuke will present a case in the next talk about a construction that involves to make a continuous extension for the whole space, but it's for other purpose, of course. But in order to present the potential here, you want unbounded potentials. So this is the thing. So we don't have to worry about not be defining the shift because we already have this with potential naturally. And also, most of the notions I'm going to present here actually are extension of notions that we already have in the standard Markov shift theory. So, for example, in the notion of conformal measures, eigenmeasures, we just, if you want to remember which is the original one for the standard case, just plug sigma A, everything is working. Except maybe for the Huel's transformation, because now it's a transformation between spaces, not operator, because you don't return to the whole space again, to the same space. But in this case, we use L1 of a non-singular measure given. And now I'm going to present these definitions. So, okay, first, the notion of conformal measures actually started with a paper of Patterson in NACTA. It was studying it uses this as a tool for solving geometrical problems and limit sets, but Denker and Urbanski adapted this notion for this space, and basically you have now you consider the Borel set here, you consider the shift map. So we call it special set every set such that when you shift it, it's still a Borel set. And it's, when restricted, the shift map is injective. And you take any measurable potential. For example, if you take the cylinder set or any Borel subset of a cylinder set, you still have, you also have a special set. So the special sets are partitioned here for the case of sigma A, for example. But here it's a little bit more complex. But you can cover the whole space by taking these elements. Okay. So a notion of when you have a potential, so here we plug this beta being the inverse of the temperature. So conformal measure in the system of Dekar-Urbansky should be a measure that satisfies this for every special set B. And also later, Starig developed a notion of these measures. And basically, there's this cylinder topology. It's a little bit different here, but also you have cylinders because you have configurations in the Cayley tree. So the topology is also generated by cylinders. And this, with this topology, I recall this is a locally compact Hausdorff space. And if you take you can define these measures, this kind of counting multiplicity of elements. So in the standard case, you just plug the cylinders here, so it's okay. So just make this Borel set intersection with cylinders, the standard cylinders, and then but here we break this in any pairwise joint measurable sets that it's restrictive, that it's contained in the Borel schema algebra to make sense this notion, and which is the union. It's the set by itself. And this notion by Starig, it's called a beta F lambda conformal measure if there exists a lambda such that this Radon-Nikodym derivative is equals to lambda e power exponential of minus beta F for almost everywhere for x and u. I mean, it's a notion inherited for a geometrical problem. Maybe if in order to look but maybe in order to look that maybe look so this because there's it's possible to construct like I saw this in some conferences and some works about this. You make up you have like a manifold. You have like a partitioning based in the Markov like cylinders and all the stuff, but I'm not. I didn't work so that. So this is everything I know about it. Okay. Also there's a notion about the Hualen's transformation, and basically, as I told you, now its transformation is not operator anymore, and when you the notion of eigenmeasure actually is pretty much the same as the previous one, the standard one, just being careful to see how you integrate the function we apply to this, okay? Okay. And also, there's another notion that's more related to the, especially when the potential is continuous, is related to the KMS states. Via the Groupoids system algebra theory. So we through the potential, given a potential, and this time I ask it to be continuous because I want a well-defined C-star algebra, C-star dynamics. And this one cocycle, it's basically the difference. You shift this. If you have an element in the groupoid, you can. You shift it the most you can for one, the most you can for after one, the other one. After that, all of them are equal. So this is everything that remains. If you think, for example, the usual notions, for example, for Markov shifts, it should be a limit of to n going to infinity. So here we don't need that because the type of relation we have here. And if one of the sides it's not possible to be shifted, just use the one side of equality. If the other side is the only one remaining, use only the other side, and it's 0 if it's like the pair, a pair in the complement of the shift. So a quasi-variant measure here, in short, I will, for this talk, I will define being basically this equation. Because I mean, this actually this is a counting measure here, and the counting measure here have a counting measure on the different. I mean, the preimages of the R, the preimages of the S. So since the groupoid is this groupoid is locally compact, Hausdorff and et al. So this pretty much fits the notion we need. This is equivalent. Okay. So the dynamics here is given by this this flow, and this when you take a conformal measure here, these are the KMS states, and this for in general cases not the only ones. Actually, these are the only ones if this is this groupoid's principle. Okay, so the first theorem in proof is equivalence that in the sense of the Markov shift, it's already happens for the sigma A. So now, if you plug this to this new space, you preserve these identities. Just for a comment, here we don't need to be F continuous in these two, but in these two, in order if you want to work with KMS states, it must be continuous. So if you plug the Denker-Urbanski notion of conformality, you can write this type of equation where inside, for example, a YA family, we have if you have a word here, each one of these YA families are countable, so the measures are atom measures restricted to this space. So basically, you call it mu of W of the word W being this CW, and basically exists a probability conformal measure if and only if this series converges. Basically, you take the count by the numbers. This is YA is countable, so this is the main condition in order to have a conformal measure. Okay, I will recall this series later. So the first thing I mentioned before is that the extremal conformal probabilities living on YA are precisely the ones living on each YA family. I'm going to show an example here that there's a case even it's uncountable many extremal states. And also we developed the topology this in order to construct a proper basis to deal with weak star limits. So basically the typical elements are countable union of cylinders and subset of YA. And this positive cylinder. So I can just ignore the inverted elements. And this is the equivalent side for the generalized one, the equivalent side of a weak convergence. And basically, the main examples here, they are connected through the weak star limits between when you take beta, going to the critical value of beta, when we have a critical value. And also you work with the pressures here. So the notion of a pressure in the Markov shift, if you just extend this to the generalized one, only counts periodical words. That means infinite elements. I mean, infinite sequences. So after a very nice experience, having very nice talks with Manfred Denker, he presented his paper with this notion of a pressure at a point. And this, because of this, you can prove under some conditions that these pressures actually they are equal. And but in order to do that, there's some condition we call it as compactness. So what S compact, I mean, if you can cover the stem by a finite union of source sets. So basically, this is a source set. Basically, take every element that arrives in A. And many examples of the theory are like this. And a sufficient condition, basically, for example, if I told you a sufficient condition for the compactness is a line of ones, a sufficient condition here is like a dual condition. It's like a column of ones, for example. It's sufficient, but not necessary. As you can see, the renew shift it's an example of that. Okay, so now we just extend the notion of variation of a function, and then now we put this condition called bounded distortion. And with the example of this, any Walters potential with the first variation finite, it's a huge family of potentials actually. And for that case, if the shift is compact and S compact, then the pressures coincide for potentials that have this condition of uniform bounded distortion. Okay, so now you have a notion of pressure, which is a proof that the Gurevich pressure is also a natural definition for pressure in the space, because you also can consider points that are outside of the standard shift. And also we have theorems about existence of this. So for example, in this case, the Gurevich pressure plays a major role here. So we have basically, if you have these conditions on the sup and infimum, you can find some regions based on the Gurevich pressure, such when you have absence and existence of these measures. If, for example, if you take let's take just a silly example. Take a constant potential. This region collapses, you have the complete description of the space. But in general, we still don't know for more general potentials. And some examples about this, when we compare the standard theory with the new theory, now you have a lot more, a lot more betas. I mean, not only one. When we have, for example, for the renew shift and potential, like being the gauge potential, I mean, potential being 1. The Gurevich pressure is actually the critical point. So now, before we had like a absence, a line of absence with one exception. Now we have like a phase transition behavior. We have nothing, and after the critical point, you have a measure. We have a conformal measure. And this is this measure is exactly the measure that we have in the case of the shift, and it's connected by the limits, the topological description I briefly told you here. Okay. But let's talk about a case where there's more than one conformal measure at the same time. So the per unit shift, you just spoil the shift, adding extra edges to the space. And this is also compact XA, but not even locally compact sigma A. And this is the matrix. So if you take the limits of this, there's two limits this time. So we have two YA families. These are the limits. Basically, you have infinite line. Just alternate the sequences. You have these only two possible limits, and then these are the limits. So now we have 1 and 2 before, remember? Now we have 1 and 2, and then another one with just 1 here. So this will start the beginning, and you can reconstruct the rest of the empty configuration, the empty word, to say. We have two empty words, and this is the difference between them. So see, if we develop a lot in the past, these are the root, another root. So in the same order, first root, second root, and first root, second root. Okay. In this case, we also have the same phenomenon. You take, for example, the gauge potential. You see these two YA families, empty word plus words ending in 1. and empty word plus words ending in 1 or 2 because you take the pair images. So this case you have 2 possibilities. And for the explicitly calculating the Uvic entropy, you have the same thing. So now you have 2 extremal measures. So you have infinite conformal measures here. And it's more interesting that if you take, for example, the Hausdorff distance, this set collapses to this point. So the limit, because you take this limit, so any branch here for every beta as a set, it's topologically collapsing. When here is the set of E beta conformal probabilities, because this is potential 1. So and this is the critical value. So it's a very strong connection between these new measures and these old measures. They're connected by limits actually. And there's another notion also, the primary renew shift. This is a powers p go to powers of pn. It's a different, more complicated way to destroy the only one family in the renew shift. And this you have countably many. And entropy, I couldn't calculate exactly, but I have a boundary that it exists. And it's between log of 2 and log of 3. And we have infinitely many extremal conformal measures, and with similar diagram. It's similar to this, but now we have countably many infinite conformal measure that collapses, probably collapses. I didn't make this account, but and we have the sense of the conformal measures before this value of entropy. And also, okay, all these examples are finite entropy. So how about infinite entropy? So during my PhD defense, Godofredo Yomi asked this question about this, and then this is I told you, it's like we put too much soda in the bread, and now we have also this. Basically, you can codify this alphabet. If you ignore this words after the first one, it's like 1, 2, 3, 4, 5. So we have like a natural bijection between this set of finite words here and the alphabet. And actually, it's connected. You have a uniqueness when you use this bijection to connect these 2 shifts. So you codify one shift into another one, and then you can codify potentials as well. Here, for example, x0 is the first coordinate in the of the word, so they have the same first coordinate. So it doesn't matter if you're looking at this or this, but when I see this, I'm looking for to the renew shift, because to the renew shift. Maybe I'm making version here, but it's okay. But the point is, if you codify one potential into another, the full shift there's a unique YA family, and the renew shift there's a unique YA family. So you connect them, and then you connect the series. So basically, the series are the same. So we can, if you have any potential here, we can convert it to a potential here. So you can study the full shift by a given potential in the renew shift. And they have the same critical values actually, and which is should be evaluated in each case. But if they exist, they are the same. And in this is a case. Remember, this is an infinite entropy case. And but even better than that, we use this result for a very one of my favorite results actually, which is how to get a universal potential. So since this YA is for the full shift is the only one YA family, and it's the biggest as possible because everything in the past, this is the natural numbers. So compared to any other matrix, this is the biggest. The empty stem configuration has the biggest root. So there's the biggest possible YA family. In this case, you can choose a potential. Actually, there are other examples, but for example, here, if you take write the potential in the full shift at this form, and then you choose the function that satisfies the on the alphabet. We can write a function in the renew shift, and then, for example, if the function f is small f is the first coordinate, for example, you have exactly the same diagram of existence and non-existence for g equals to 1 for this potential in the full shift, and then it's basically the same diagram for the renew shift. Okay, so this kind becomes if you we could choose x0 as well here, but we choose a more smooth. A smaller potential to get a bigger family of potentials possible, but you can choose your favorite one. But basically, this full shift series bounds any other shift because this is the biggest family as possible. And because of that, there's the interesting example when you have uncountably many conformal measures. So basically, we construct it like this. We order by period. Doesn't matter the ordering between two matrices is the same period. So period 1, period 2, period 3. And then you pick everyone in the period 2, everyone with period 3, the minimum period. And then you can construct like this shift, for example. This is period 1. Exclude the 0 because you want it transitive. Alternating, now alternate period 3 minimum 1, and then go forever. This is a very special shift with very good properties because this is basically the exception for almost every rule because this is topologically mixing actually. But remember, and I told you that when sigma A is locally compact, XA should be equal to sigma A. In this case, we have this is an example. For example, it's not every XA which is only locally compact but not compact that comes from a not even locally compact standard shift. So this is a good example for that. Also. Every column, the proof that it's non-locally compact, it's because it's equivalent to be Xa is compact if and only if is not compact actually. If and only if one of the limits of the matrix is the matrix 0. This actually is a result of a paper and Rui and Marcelo. And this is the proof that this is not locally compact. But every sequence possible, every column here is a limit of sequence here. So we have uncountably many empty state configuration. Any subset which is not empty is an empty state configuration. And applying this result of the, for example, we could take log of x0 plus 1, but this is also not. For beta greater than log of 2, each conformal measure, by applying the previous result about the codification, the universal potential, we have one extremal conformal measure for each YA family. So we have an uncountably infinite set of extremal measures. And finally, we also have by using existence theorem by Duncan and Yuri on the renew shift, we also have a new type of phase transition. It's called length type phase transition. What is a length type phase transition? We have infinite words and finite words. So basically, the measure, the eigenmeasure this time, and this with lambda being the exponential of the pressure, it exists for every beta, but it's only one, and it changes from the sigma A to YA for after a critical value. And the critical value, it belongs to the sigma A. It lives in sigma A. So basically, this is just all the conditions we have for the renew shift. And so we know the pressure coincides. everything works. And this is I would say this was a final theorem. So basically, for the generalized renewal shift for this potential, we have this eigenmeasure. It's classical measure, we say, because this, the lambda is exponential of the pressure. Remember that Keim states is like a pressure zero state. So if you see the identity presented before, because there it's not eigenmeasure, it's a fixed point measure. But here we have this this measure existing all the time, this eigenmeasure, and it changes the space. So now a measure that was living in the renewal shift goes to the standard shift goes to the new part of the space. So basically this is the diagram. So this is what we have before before the generalized shift. This is when you have in the when you look to the generalized shift. So these are the measures not detected by the theory, and these are the KMS states. So this is a bibliography. If I hope probably I pass a little bit of the time, I think. 2 minutes? 3? Yeah, so it was great. So thank you very much.
You talk about conformal metrics, right? So
Yeah.
You were not the one to define.
Exactly.
They come from the urbanity definition.
Yes.
Here's the thing. The inspiration for them was from a complex geometry.
Yes.
So that, sorry,
Yes.
hyperbolic geometry, yes. And there's a notion of like the fusion group. And these measures, they kind of relate very well with these homomorphic maps on these spaces. So that's in the inspiration.
Yeah. Yeah, so this is basically the original work for the first time that this notion appeared. It was actually a Patterson paper. So
They worked in the paper, yes.
yeah.
And I think Dennis the guy won the Apple Prize.
Oh yes, sorry, yes, but he used this as a technique for solve the problem that Rodrigo Prozino described. Yeah, exactly.
And conformal measures play a very important role in relation to the mechanics.
So there's present in the slide in the
Sure.
Just to point out that we have measured living the finite work and going to something that.
Oh yeah, sure. Here.
No, okay, here also. We did the convergence here also, right?
Yes. We have this connected by convergence also as well.
Yeah, because this is okay, because we didn't kind of right highlight this, but one of the things that we found that is very kind of surprising, the measures in the red part they give mass only for finite work, because this space is kind of the original space plus the finite words. They are leaving the same globally compact space, and the measures in the red part give mass only for finite words, and the measures in the white part give mass only for the U-coefficient space.
Yeah.
So we are able to prove that the measures living in very different space are going to the Uvic topology to this original one. This was and another thing that this Thiago discovered, because there is a paper of Fontaine that he studied for KMS for graph algebras. And then he proved that there is a relation between extreme conformal KMS weights and the symbols which are equilibrium. So in the first example, for the real shift, we found the same. So we are very, very sad. We find the paper of Klaus and we just recovered his result. Some moment was very bad for us. But after Thiago invented this kind of YA family, which is a different object. So if you look for the real shift, match. So we are in the same place as Klaus Thompson. So one is thermoconformal measure for each symbol conformal. So each array family corresponds to each extreme conformal. So
Yeah.
that's why I asked about we have a geometric characterization looking for the matrix for which are the conformal. It's very concrete. It's very not usual.
Exactly. And
You can see exactly.
exactly, and it gets you see the very part exposed of this difference between these two notions, these two algebras, is because this case, for example, we have uncountably many extreme states. So it's in fact the different object that codifies the new extreme ones. Just a comment. This thing that is very interesting because these are KMS states, because if you evaluate the pressure here, it's the case to zero and keep zero forever. So this is why it's KMS state, because pressure zero eigenmeasure.
Yes, conformal measure corresponds to the base of the pressure.
Exactly. Exactly.
So any further comments? No.
Thank you very much.
Thank you for introducing me. And Thank you for inviting me this wonderful conference. So, yeah, I am Keisuke Yoshida from Japan. I mean, I came from the opposite from the opposite side of the earth, and yes, this work is based on joint work with Yuta Michimoto and Yushi Nakano and Hisayoshi Toyokawa. And me and Michimoto, Nakano, Toyokawa can be divided into two groups. And Nakano and Toyokawa is team dynamical system. And Michimoto and me is team operator algebra. And I will talk about the Markov shift, which is very similar to the renewal shift. And when this study started, Nakano and Toyokawa brings me the PhD test of Thiago Raszeja. And I mean, this study is strongly motivated by the work Bissagot, Excel, and Plauciano, and Raszeja. And so this is the outlines of the talk. I will start from fixing the notations, and I will introduce the motivation. And next, I will show the preliminaries. But the some of preliminaries are already explained by the Raszeja. And next, I am talk about generalized and non-commutative shift map in some special case. Yes, Thiago talked the very general case, but my talk is limited to very limited case. Yeah, my talk is not general one. And at the last, I show a computation of entropies, but this part is very rough sketch. So precision is often lost. So I am sorry about the loss of precision in here. So and first we fix the notations and introduce the motivation. So I consider the Markov shift. I mean we consider the 0-1 matrix. 0-1 matrix is the matrix whose entry is 0 or 1. And sometimes the matrix is finite matrix, and but matrix can be infinite ones. And if we have a 0-1 matrix, that induces the Markov shift space. Markov shift space is the space of unilateral infinite sequence of the symbols. And we define the admixture word or formatting word. And admixture word is defined to be like this. And Markov shift space is the space of infinite words. And on the other hand, one can consider the finite admixture words of a set of finite admixture words. In this talk, we write capital sigma A with star for the set of finite admixture words. In my talk, E is the empty word, and one can define the shift map. Shift map deletes the first letter of the sequence and move everything to the left side. And I'm sorry to I start the sequence x1. On the other hand, Thiago starts the sequence x0, which can confusing someone, but okay, I hope this is no problem. And here is the table of notations. And A is a transition matrix. Sometimes it's a finite, and sometimes it's infinite. And capital sigma A is Markov shift space, and capital sigma A with the star is a set of finite administrative words, and small sigma A is shift map. And OA, I write OA for the C-star algebras. That is Kunz algebra in the finite case. And infinite case, one should generalize the Kunz-Krieger algebra, and that is XL algebra. And sometimes we consider the commutative C-star subalgebra of OA. In finite case, that is C of capital sigma A. I mean, the ring of the continuous functions on Markov shift space. But infinite case, that is the Cartan subalgebra of OA. But in today's talk, we do not know what is Cartan. Yeah, there is some kinds of special commutative algebra. And capital XA is capital sigma A in the finite case. And in the infinite case, character space of DA is denoted by XA. And we only, infinite case, we consider the generalized Swift map, which is already introduced by the Thiago Raszeja. And last, I introduced the non-commutative Swift maps. And yeah, in finite case, this one is always constructed. We can always construct the non-commutative Swift map. But infinite case, and maybe sometimes we cannot construct a non-commutative Swift map. I am talking about the situation the non-commutative Swift map can be constructed. And here is the standard hypothesis. That is the Swift map is topological mixing, and no zero rows exist. Zero rows are not exist, and zero columns are not exist. So to introduce the motivation, please let me explain the finite symbol case. So to consider the finite symbol case, let the symbol set is 1, 2, 3, 4, 5, 6, n, n. So we consider the Kunz-Krieger algebra. That is the universal C-star algebra, and generated by the partial isometries S1, S2, S3, blah blah blah, Sn, with the following relation. Yeah, in today's talk, we do not have to what is the universal C-star algebra. Yeah, this is we consider the C-star algebra that is generated by the partial isometries with these relations. So this C-star algebra is called Kunz-Krieger algebra. And for notation simplicity, and for the finite administrative word, we write partial isometry correspond to this finite administrative word like this. Yes, and for the empty word, yeah, we define SE to be the 1. And one can consider the commutative C-star subalgebra DA of OA, which is given by, which is generated by the projections like this form. Then it is well known that I think algebra of continuous functions on Markov shift space is isomorphic to this commutative algebra. So we regard the continuous algebra of continuous functions as the C-star subalgebra of Kunz-Krieger algebra. And on the Kunz-Krieger algebra, one can define the U-shaping map gamma L that is given by like this form, and elements is sandwiched with partial isometries and its star. And because we have a continuous map on continuous shift map on the Markov shift space, we can consider the product operator. That is, we write the product operator for sigma S star. That is given by this form. And for any continuous function, we have these equations. Of course, this extension holds in the under the identification of the continuous function with BA. And and for the I want to talk the entropy, and the entropy viewpoint of entropy. The following theorem is known. The theorem is given by Boca and Goldstein. That is, if A is irreducible and not a permutation matrix, then non-commutative. This is non-commutative entropy, and this is classical entropy. I mean, non-commutative one and classical one coincides. So I think this is a natural question that what happens in the infinite case. Yeah, I want to imitate this theorem in infinite case. So go ahead to the preliminaries. Given by Brown.
Cheating also that they change it a little bit, seems better than the constant. Because there is never, and I guess that the constant it was the first one, but after I think the constant cheating it was better in some sense for the environment maps and things like that. I don't believe that. Okay, you have the definition here, right?
Yes. Non-commutative entropy. The definition of non-commutative entropy is given in the later. I will show the this one. I will show. Yeah. So yes, I want to consider the infinite case. So from now on, the matrix A is already infinite matrix. And the symbols are already is a set of the natural numbers. And to introduce the Excel-like algebra, we consider that we use these notations. So the Excel-like algebra is Kunz-Krieger algebras for infinite matrix, and we use the same symbol for Excel-like algebra OA. That is the universal C-star algebra generated by the partial isometries, but the partial isometries is the infinite countable partial isometries with the following relations. Here is the following relations. In this talk, we use the third one and fourth one, only third one and fourth one. And so we use several times this equation. So we note this. Yeah, for the reminder. So I mean, this is equivalent to this Poisson isometry is not 0. And equivalent to two lengths word ij is admissive. we use this tool in several times, maybe implicitly. So from now on, to simplify the situation, we assume that there exists that the row that is infinitely many one, more strongly that has finitely many zero. Then OA is the extra algebra OA is unital because one has this equation. This equation is from the fourth one, yes. And but if we assume this, we can consider the unital sister algebra. But on the other hand, sigma A cannot be locally compact. So the algebra of continuous functions on Markov shift map run away from sister algebra theory. So we have to say bye-bye to C of. So go ahead to the generalized system map and non-commutative system map. From now on, we use this notation to denote the column. We use CI. To denote the row, we use RI. More precisely, if we have the infinite matrix, so cool. Column. And CI is the set of indices whose whose entry is 1, and Ri is set of indices defined to each row whose index is 1. So I introduced the definition, and a natural number is said to be an infinite type letter. To be honest, I want to say a finite emitter, but this definition is different from the study of for Thiago one. So I use the word finite type letter and infinite letter, and that anyway, and a finite type letter is the natural number such that I row has finitely many ones. On the other hand, a infinite type letter is the natural number such that ith row has finitely many zeros. And if I is an infinite type letter, we have the following. And actually, this sum is not the infinite sum, because only finitely many j, aij equals to 1. And if I is an infinite type letter, so we have this equation. And here, this is not infinite sum because but for finitely many j's, aij is equals to 0. And we consider this very strong condition. That is, every natural number is A infinite type letter or A infinite type letter. So I show the example that satisfying the condition C1. That is linear shift. Yeah, linear shift has the A finite type letter or A infinite type letter. The first row is a finite. First row is A infinite letter, and remaining rows are A finite letters. But the condition C1 is very strong, so we can find the counterexample easily, and that is pair linear shift. That is already introduced by Thiago Raszeja. This looks like linear shift, but the difference appears in the second row. Here, second row, we have infinitely many zeros and infinitely many ones. Yeah, that is bad for me. Yes, this condition C1 is very strong, but actually I have no idea to construct the non-commutative shift map without C1. So let me go ahead. And I introduced what C1 implies. In general, OA is described this like this. But if we assume the C1, so OA has a more simple form. Yes. And note that S alpha, S beta star can denote the unit because, yes, we defined SE to be 1. Yeah. This right hand side includes the unit. And move to the embedding of Markov shift map into the character space. Yeah, that is already explained by Raszeja. We give a vector state construction of XA. I give a vector state construction of XA. That is consider the representation of X-block algebra given by this form. Actually, we use universality here, but no. Yes, but yeah, we don't take care of that. Yes, for each element in Markov shift space, we define the vector state like this. Actually, the restriction of this state to the commutative C-star algebra. This one become a character. So, yeah, and we remember the lemma, which is introduced by the Thiago Raszeja. The map X to this vector, to restriction of this vector state gives a continuous embedding of Markov shift space into character space. So we regard Markov shift space as a subspace of character space. And we want to consider the complement of sigma A. For this purpose, set YA prime. That is a set of finite bars which ends in the A infinite type letter. And consider the representation. Consider another representation on this L2 space. So given by, this is similar to the previous slide one. But because we have to consider the empty set, we define like this. And yes, one have to check this formula gives the representation. But we are assuming very strong condition C1. So this formula defines the representations. And once we get the representation, so we define vector state tau alpha, similar to the previous slide one. And similarly, the restriction of tau alpha become a character. And set the complement of sigma A in the character space to YA. And assume that C1 holds for A. Then YA can be written like this form. This is a very simple case of the proposition that was introduced by the Thiago Raszeja. And I explain what we want. And let 5 is a Gelfand-Naimark star isomorphism from the commutative Cardan C-star subalgebra from continuous rings of continuous algebras. And what we construct is the continuous map that is defined on full space and non-commutative shift map that is defined on Excel-like algebra, such that non-commutative shift map coincides with the generalized shift map in this sense. And here, to ensure that this function is continuous and defined on full space, we want to define the generalized shift map to be a continuous map on full space. This is the commutative diagram form of the previous slide. So we define the generalized shift map like this. We already know XA is given by vector states. We define for the sigma A like this, and we define the generalized shift map for the YA dash like this, and for the character which corresponds to the empty stem, we define like this. And I explain. Yes, and actually, condition one implies that condition one implies the uniqueness of the empty stem. So because the yes. And we give observations. So let's consider the Groupoids set that can be called the generalized cylinder set. That is the set of characters and that sends SI star to 1. It is easy to see that this is the Groupoids set in character space. And if this shift map is continuous, then this guy should be Groupoids set. And now XA is compact space. So this guy should be compact open set. And observe the right hand side. This one should be compact. So Ci should be the finite set. Thus, we consider the second condition, that is C2 for any natural number. We have the set of indices whose entry is 1 is finite set. And yes, the columns are finite. Yes, so yeah, one can call this condition column finiteness. So if we assume the column finiteness, then we can construct the non-commutative shift map. Because, yes, to imitate the Kunz-Krieger case, maybe this is natural considering this form, but the problem is this can be infinite sum. But we assuming the column finiteness, luckily this one is finite sum because yeah, this set is a finite set and this is also the finite set. So this sum given by finite sum. And now we define a linear map gamma n on the dense subspace of the X-Rack algebra by like this for the generators that is not equals to 1, and for the unit we defined 1 tends to 1. Then yes, we define the linear map on the dense space. We have to extend this map. So we have to check the continuity of gamma A. But this can be done if we assume the condition 1 and condition 2. So we can extend the gamma A to for entire algebra of OA. And furthermore, this gamma A is UCP map. And moreover, we have the fact that we want it. I mean, the image of the commutative C-star subalgebra included in commutative C-star subalgebra, and the generalized shift map can be continuous, and we have the we have this equation. So we succeed to imitate the Kunz-Krieger case. And yes, we introduce the condition C1 and C2. So yes, I have to explain when condition C1 and C2 hold, and linear shift case and condition C1 and C2 hold. So yes, because if the linear shift, in the linear shift case, any columns have only 2 ones. Yes, so linear shift is the column finite case. And yes, yeah, I show a sketch of computation of entropies. So here is the definition of non-commutative entropy. But to be honest, this is the very rough one. And let me explain for the general case. Let capital A be exact C-star algebra. Please don't consider what is exact C-star algebra, and gamma be the CP map. CP means completely positive. And consider the finite set omega in C-star algebra. And we want to compute the size of this set by we want to compute the size of this set by the sufficiently nice finitely dimensional approximations. Finitely dimensional approximation, I mean finitely dimensional approximation is this formula. Here, pi is the faithful representation of the C-star algebra, and phi and psi are CCP map. And composition of pi, phi and psi close to pi in a pointwise norm continuities. I mean the pointwise norm topology sense. Why we have to consider the finite dimensional C-star algebra? That is matrix algebra. This guy is non-commutative. The non-commutative is the non-commutative division of 1. So, and we compute the size of this matrix. We compute the gross of size of this matrix and compare the exponential. Compared to the exponential, we call this guy non-commutative topological entropy. Yeah, here is more precise definition, but here I wanted to say is to estimate the non-commutative topological entropy, we have to consider the sufficiently nice finite dimensional approximation. We need finite dimensional approximation. Yes, go to the next page. And I introduce the Griffiths entropy. Because more classical entropy does not behave because we are considering the case sigma A is not the compact. Instead, we consider the following Griffiths entropy. In our case, Griffiths entropy is given by like this. And one have to consider the question, non-competitive entropy and Griffiths entropy are same. We consider this problem, but thanks to the variational principle, we have the one-way inequality. So Griffiths entropy is smaller than non-competitive entropy. So we consider the opposite side hold. And again, to estimate the non-competitive topological entropy, we need some finite dimensional approximation. And in a Kuntz-Krieger algebra, in a finite dimensional case, and Boca and Goldstein uses this set. This is the set of administrative bars whose length equals to m. Yeah, this set works well in the finite case. I think there is two important things in finite simple case. One is the size of matrix is estimated by the cardinality of this set. Thanks to this inequality, one can estimate the non-competitive entropy by this limit. And another important thing is these equations. So finite sum of these projections equals to 1. This is the source of nice approximation. So let's imitate this one. But we have a problem in infinite symbol case because the set of admissible words whose length is m is an infinite set. So to consider the finite set, instead we consider this set. This set is a set of finite admissible words whose length is m, and the most left letter is smaller than n. Since we are assuming the column finiteness, this set can be this set is always a finite set. Moreover, a computation shows that gravity entropy is very similar to the limit of this set. Oh, I'm sorry. I forgot. I forgot this guy. Yeah. And log. I'm sorry. But actually, we have some error. The error is given by the max natural number, which is appear in the most left side. Yeah, but though in general, this I cannot be 0. For the linear shift, actually, this I equals to 0 because this one equals to n plus m minus 1. Yeah, this is polynomial, and we compare to the exponential. So this I equals to 0. Yes, and what I want to say, this LMN can works well, but how we have a very very bad problem. That is, this finite sum of projection does not equals to 1. So using LMN, we cannot approximate by the we do not have the nice approximations. So we modify the problem by finiting the infinite symbols. But finiting the infinite symbol is very complicated. So I'm sorry that yeah, we only have several pages, but from now on the slides are very complicated. I'm sorry. And yeah, so let's finitize infinite symbols by using the modified column finiteness. So we assume that there exists a finite division of natural numbers. I mean the word division, I mean they are mutually disjoint. And furthermore, I define to be they have the how to say okay how to diagonalizing property. Diagonalizes. No, yeah, I'm sorry. Yeah. I want to say. I actually, I forgot the English word. And what I want is this one. Oh, maybe there is. Oh, okay. I remember the English word, orthogonal. well, I want to orthogonalizing the, I want to orthogonalize. So I consider the first one. Then the second one is just a reindex property. So the first half division, they have the infinite natural numbers, and they have finite natural numbers. And actually, this condition C2 dash implies C2. So this one is modified column finiteness. And for the by the first condition, we have the orthogonalization of partial isometries. So I mean, if I and J contained in same partition, one always have if I does not equal to J, yeah, they are always diagonalized. Oh, orthogonal. Okay, I'm sorry. Yeah, English words sometimes is difficult for me. And because they are in this partition, we also have this one. So, if we consider the infinite sum, like this, this can make sense in some Hilbert spaces, because range projections and domain projections are also orthogonalized. So, using the strong operator topology in some nice Hilbert space, we can consider the new partial isometry given by infinite sum like this. Here, what is a nice Hilbert space? To get a nice Hilbert space, we assume the existence of KMS state and using the GNS representation. So we assume condition 3, there exists a KMS state phi for the canonical gauge action and inverse temperature with the sum of these guys equals to 1. Some experts know that this KMS set comes from the conformal measure, which is living on sigma A. And using this partial isometries, we modify LMN to this one. Yeah, here we are what we are doing, and replace the right side ones by this new words. We replace the right side words by with this new words. And then, if we consider the modified this modified finite set, then we have fortunately these equations. So we can approximate nicely. But we replace element to the element bar. So we consider the difference between these two sets. The difference is given partially given by this limit. And so finally, we have the main theorem. Assumes that there exists at least one infinite typewriter and condition C1, C2 prime, C3, and furthermore, we need C4 for the technical reason. C4 is this one. And then we have the opposite side of comparing the non-competitive entropy and the gravity entropy. Yes, we have 3 error terms, log PA, and I, and D. PA is given by the condition C2 prime. And this is the main theorem. So, at the last of my talk, I give an example. So consider the renewal shift. Then we consider the very natural division, the set of finite typewriters and A infinite typewriters. This division shows that PA equal H. Sorry, H is Japanese, 1. And the equation, this equation shows that D equals to 0. And we have already seen that I equals to 0. So we get this equation. I mean, non-commutative entropy and gravity entropy are same. And as introduced by, as shown by Raszeja, this gravity entropy equals to log 2. So we have the non-commutative entropy that equals to log 2. Okay, that's all. Thank you for listening.
The non-commutative entropy, is this coming from a paper from CARE?
Yes. Originally, I think so. But for the exact C-star algebra, paper by Brown, I think.
I think Brown defined the entropy that you are using, right?
Yes.
Which Brown is this?
Not a book. Paper is.
But in the paper of Karen Pizzari, they studied the pressure. You stop in the entropy, right? You was able to do the pressure also?
I think so, but I try first, consider the entropy, and I want to go to the pressure to the next in the next stage.
The general case,
Yeah.
it is possible to define a non-commutative shift map on a subset of the algebra.
In the general case, okay. Yes. Yeah, I'm sorry, I don't have any idea. So I will consider after coming back to Japan.
But what is the reference for this shift map?
I mean, in Renault's paper, he already introduces the partially defined shift map.
Yes.
Right? So at least in the commutative case, you can view functions of compact supports on the domain of the shift.
Yes.
So that gives you stars.
Yes. Maybe considering regards eccentric algebra as Groupoid sister algebra, and consider the continuous functions with compact support on the domain of generalized system map. Yeah, that can make sense, but I did not try.
Another thing which might make sense is that Kunstkrieger case,
Mhm.
the shift map is a sum.
Yes.
Sum of SI.
Yes.
So you could take the subset of elements such that the sum converges.
Mhm. Yes. Yes, thank you.
The map might not be bounded.
Yes.
I think that if I'm not mistaken, the definition of the entropy
Yes.
could apply for an unbounded map.
Yes, we need this. Yes.
You won't have to approximate on a finite set of elements.
Yeah.
And only the dimension of the matrix algebra is relevant.
Yes.
So boundedness of the map is relevant.
Yes.
Maybe not work with the for the special, right? You need a completely positive.
This is going to be positive in some sense.
Mhm.
But,
Yes. Maybe we have to consider positive but unbounded map.
Sorry, I wanted to make a comment. This presentation for the Kunstkrieger algebra for infinite matrices. We and I came up with this downstairs 25 years ago. And the path towards finding those relations started with your condition C1,
Yeah.
followed with your condition C2, and followed with your condition C2 prime. So we started finding the relations exactly as your conditions appear. Because we said, well, we don't know what the relations are, but they have to contain these in this case, and they have to contain those in that case, and they have to contain. So what you're retracing is the path that led to the full set of relations. So I'm hopeful that if you keep working, you will get the general form that way.
Oh.
And you can get all the relations if you keep seeing.
Oh, thank you. That is surprising. I did not know that.
But did you finish the paper here or you were there? But you had a position in Australia.
Yeah, I was there.
I see. Any more questions or comments? Okay, let's thank
Yes, thank you, and I'd like to thank the organizers for this opportunity to speak here. So I am firmly in the classical side of the statistical mechanics community, but I've been learning quite a lot of the quantum side in this conference. So thanks again for the organizers for giving me this opportunity. And it's also my first time in Brazil, and in fact, even more embarrassingly, it's the first time below the equator. So I'm really thankful for this experience. Okay, so what I'm going to talk about is joint work with my collaborator, Inon Spinkas. So he's still in UBC, but he will move to Tel Aviv soon. And this work is sort of part of a general theme in an area I'm involved in. And it's kind of fascinating to me since my PhD, that when you have a stochastic process, and so sort of the general theme is how does the stochastic process change behavior if you change the underlying geometry of the graph? Okay, so there's this theme of results. So the two types of graph, there's various names. One side is parabolic, the other side is hyperbolic. In this talk, we are going to talk about amenable versus non-amenable. And the point is that whenever you take a stochastic process, the sort of qualitative behavior drastically changes when you go from one geometry to the other. Okay, and there's been a lot of work or theorems of this kind of theme. So there's a bunch of I listed a bunch of stochastic processes. I'm not going to define any of them. This is just to give you some idea of the type of processes people work on. This talk is going to be about two types of two notions in probability and statistical mechanics, and we'll try to see when you change the geometry, how these sort of specific questions, the answers change when you change the geometry. Okay, so the two notions are stochastic domination, which is like from elementary probability, and the second notion is finitary factors of IRD, which borrows its ideas from ergodic theory. So I'm going to define all of these notions. So the plan is to first talk about stochastic domination and the results, and then talk about finitary factors of IRD and the results, and then base some ideas of the proofs. Okay, but the main motivation of this work came from some questions in this area. So I'll try my best to explain what it means. Okay, so the first part is going to be very elementary, so I hope to not lose any of you during the first part of the talk. So we have a finite, a partially ordered set. Think finite for the moment, and you have two random variables. We say the x stochastically dominates y if you can define them in the same probability space, so that with probability one of them is bigger than the other using this ordering. Okay, and mostly we'll work with sets of this type. So now you can, so of a state space which is like 0, 1 to the v. So if I put plus minus to the v, then you could immediately recognize this as the state space of Ising model, for example. But this is going to be the general the setup, and v is usually going to be some countable set, usually a vertex set of some graph. And the ordering we'll consider is two configurations. So omega and omega prime. Omega is less than omega prime if coordinate wise they are less in this ordering in S. Okay, so in here the S is well, in here it's just 0 and 1. So if omega v is less than omega v prime, then we say for every v, then we say that the omega is less than omega prime. Okay, so that's the ordering. And okay, so let's start with something extremely elementary. So we have two Bernoulli random variables with parameters p and p prime. P is bigger than p prime. Does x stochastically dominate y? So can we put them in the same probability space so that x is bigger than y? This is of course very easy. Here is a way to do it. You just define the two coordinates to be 1, 1 with probability p prime, 1, 0 with probability p minus p prime, and 0, 0 with the remaining probability. And it's very easy to see that when you add up the first two coordinates, you get p, which is the probability that x is 1. So, and you can check that this indeed is a nice coupling. And here, of course, the first coordinate is always bigger than the second coordinate. Okay, so this gives you a very elementary way to prove that X stochastically dominates Y. Right. So far, so good. Certainly. Please feel free to stop and ask questions. Okay. All right. So let's make it a little bit more complex. So suppose we have a collection of Bernoulli random variables. So let's start with a single let's start with a collection xi p where p varies over this interval 0, 1. Now question is, can we put all of them together such that the ordering is maintained? Okay, so xi p is less than xi p prime whenever p less than p prime. And I'm putting up this figure because if you have a bunch of these independent xi p's, then you can sort of think of it geometrically as what is known as a Bernoulli percolation model. So you have a Bernoulli random variable 1 for each edge. So you fix a p, and suppose you have some IID collection of Bernoulli random variables 1 for each edge, and you open an edge if xi is 1 and you don't open it if xi is 0, then that gives you a random subgraph of this thing. This is called a Bernoulli percolation. And the question is if you vary p, can you couple them so that the subgraphs sort of increase, right? And the answer to this question is yes, indeed. If you change p, you can couple these pictures together so that for larger p, the subgraph is bigger than the smaller one, and it's actually quite easy to do it. So just take IID uniform random variables on every edge and define xi p to be 1 if this uniform variable is less than p and 0 otherwise. Okay, and that gives you a bunch of IID random variables, each with distribution Bernoulli p. And now if you change p, the xi p's always increase if you increase p, and that gives you a coupling which works simultaneously for all p and for all IID random variables. Okay, okay, good. So when things are independent, it's still nice. Okay, so now let's mix things up a little bit more. So now imagine we have a Bernoulli site percolation on a graph. So imagine instead of having opening an edge, you open a site, you color them say black or white with if the xi is 1 or 0. Okay, and now you define this random variable which we call a percolation set. So omega v infinity we say is 1 if v is connected to infinity. So if v is in an infinite component. Okay, so if you go back to this picture, I mean it's not infinite, but imagine that this cluster sort of goes up all the way to infinity, then all the vertices in here will have omega v infinity, the value will be 1, and otherwise it's 0. So if you're not connected to infinity, you're 0. If you're connected to infinity, you're 1. Okay, so it's a slightly modified function of an IID Bernoulli random variable. It's dependent. If some vertex is 1, its neighbor has a very high chance to be 1, because once you're connected to your neighbor, you're already 1 because you're already connected to infinity, the neighbor. And then we ask the same question: does this dominate a Bernoulli p prime percolation? So if you start with a Bernoulli p, and you look at these 0, 1 valued variables, do you dominate a Bernoulli p prime random variable? And if so, so imagine p is very close to 1, so you have lots and lots of open vertices. Can you dominate a Bernoulli p prime where p prime is also close to 1? But if not, so what's the largest such p prime that you can dominate? That's the question. Okay. Okay, and so when we first came up with this question, our intuition was that yeah, I mean it's going to dominate a big p prime because you have lots of open edges. So why not? Many things are open, but it turns out that the answer depends on the geometry. So that's where this kind of the project started. So here's an example. So your graph is Z2, okay, it's a square lattice, right? So in this case, we claim that the largest p prime that you can dominate is 0. Okay, you cannot dominate any positive Bernoulli p prime, and here is a proof. So take a big box. Okay, now if this set omega infinity dominates a Bernoulli p prime, then we have this inequality here. So omega infinity lambda equivalent to 0 means that everybody in the box is 0. So if everybody in the box is 0, and if it dominated a Bernoulli p prime, then the Bernoulli p prime also everybody must be 0, and that has this probability 1 minus p prime to the size of lambda, right? But on the other hand, notice the following. If on the boundary of the box you change everything to 0, then the inside is completely cut off from infinity. So with this cost, 1 minus p to the boundary of the box, you can make everything inside 0 for free, right? So you get this inequality, and okay, if you take 1 over mod lambda power on both sides and let lambda go to infinity, because this is true for every box, then you immediately get that p prime has to be 0. You get on the right hand side, this side will converge to 1 if you sort of take 1 over mod lambda power, and that would mean that the right hand side goes to 1, which can only mean that p prime is 0. Okay, so here if the point is that this proof actually will work on any graph. I took Z2, but it will work on any graph where the boundary is much smaller than the bulk for a collection over a sequence. If you have a sequence of sets where the boundary is much smaller than the bulk, then this proof will just go through, right? So actually, we're going to define amenability, and amenability will mean exactly this. Once you have a sequence of lambdas such that the boundary is much smaller than the volume, then we call the graph amenable. Otherwise, non-amenable. All right. Okay. So okay, but is it false for? I mean, is it 0 for any graph, right? So the other type of geometry, sort of a typical example we think of other than Z2 is a regular tree. Okay, so you can take a binary tree and ask the same question, right? What if is there a positive p prime? Let's start with that, such that you dominate that positive p prime, right? Okay, but except for like simple situations like Bernoulli percolation, how would you even go about proving domination, right? How would you prove that a bunch of variables dominate the other? Well, here is a general strategy. So first, you suppose you have a triplet of random variables, and we want to show that this dominates x prime, y prime, z prime, and here again the domination means coordinate wise. So first prove that x dominates x prime. Okay, somehow let's say you prove it, and then you look at the conditional distribution of y prime given this pair x and x prime, and you prove that this conditional distribution still dominates it as long as your pair x and x prime is on this set where the first coordinate is bigger than the other. So no matter what the values here are, as long as this inequality is satisfied, if you can prove this domination, then you have done your second level of domination, and then this will prove that this pair xy will dominate x prime y prime, and then you continue, right? So you go step by step. You start with one variable, prove domination, and then conditioned on whatever the value of that pair is, as long as one is bigger than the other, prove the second variable domination, and you go on, and then it can give you, I mean, okay, I did another level, but if you iterate this, it will give you that, like for any finite vector at least, you can prove domination if you go through this strategy. Okay, that's one strategy, but of course proving things, these things will depend on the specific situation. Okay, so here is the proof, a proof that on a 3 regular tree, at least p prime is strictly positive. Okay, okay, so here is a quantity. It says that it's asking for the probability. So here is my vertex v. It's a bit small, but let me point to it. So here is a vertex v, and I'm asking for the probability that this vertex is 1 conditioned on whatever you see in this orange area. Okay, so imagine you have dominated everything in the orange area, and you ask what is the probability that this vertex is 1. So this xv is so I denoted by omega v in the previous slide, but xv is the indicator that you connected to infinity, and we want to lower bound this quantity no matter what the past is, right? So it's some function of the past. Okay, now here is a lower bound. So imagine this is w. Okay, so if xw is 1, that means w is connected to infinity. Okay, so then if v is open, which has probability p, then you're already connected to infinity because w is already connected to infinity. So that's at least p. And if this is 0, this w, so it's not connected to infinity, well, then there is some chance that actually the percolation value is 0. Okay, so it's 1 minus p chance. And on that event, there is some probability that the percolation percolates through this tree, to the future, sort of. Okay, and that is some probability theta p. Theta p is strictly positive if p is bigger than pc. So there is this chance that so phi of the past, no matter what the value is lower bounded by this quantity. Okay, and so overall, what we get is that this this quantity stochastically dominates a Bernoulli with parameter 1 minus p times theta p. So that's a very crude bound, but it's still positive. Theta p is strictly positive. Okay, so the conclusion is that when you change the geometry, so when we were in ZD, then the highest Bernoulli you could dominate was 0 probability, and here it's some positive probability. It's not 0. Okay, so that's the kind of dichotomy theorems we are going for here. So there will be more theorems like this, but this is sort of the basic, a very basic level of the type of arguments that we do. Okay, any questions so far? Does this make sense? Okay, good. Okay, so note one thing here, that if p is very close to 1, the parameter, the probability that you dominate is actually going to 0. Okay, so actually the Bernoulli you're dominating is becoming sparser and sparser as you let the probability, as you let the Bernoulli variables get denser and denser. Okay, so the original Bernoulli variables get denser and denser, which is a bit disappointing, because our initial guess was that you would dominate like a very high density Bernoulli. Okay, you get something positive, but still it's a bit unsatisfactory. But anyway, let me go ahead and make these definitions. So it's a very natural definition at this point. If you have a stochastic process, define p of x to be the largest p such that x dominates a Bernoulli p. Okay, and okay, so for the sake of the next part of the talk, let me also give you a definition which well, it's a bit out of the blue at the moment, but it will make sense later in the talk, I promise. So we say that x invariantly dominates Bernoulli p. So imagine your x is a stochastic process in a graph. Imagine easing on a graph, and we say that x will invariantly dominate Bernoulli p if you can construct the coupling so that x is bigger than the Bernoulli. That coupling is invariant with respect to translations of the graph. Okay, so or any automorphism of the graph. So invariant means invariant under the group of certain subgraph or subclass or the whole group of automorphisms of the graph. Okay, so this is a stronger notion. Of course, this inequality is kind of trivial because we are asking for more here. Okay, so those are two definitions. The theorems will be in terms of these definitions. Okay, and now let me quantify what I mean by different geometries. So, so this is a notion. So let me introduce this notion of a Chigger constant. So it's a, I mean, there has been definitions like this in group theory and so on. But for us, it's like it's a definition which will work on any graph. So if you take a graph, you simply look at the infimum of this quantity. So so you look at the smallest possible ratio of the boundary over the volume over all possible sets. Okay. Of course, my graph is infinite here. If it's finite, you need to tweak the definition a little bit, but you have infinite graph. So you can immediately, or you can check easily, that if you have a regular tree, then this quantity is strictly positive because the boundary is kind of constant proportion of the volume. A calculation you can do. On Z2, it's the boundary is like if you take a box, the boundary is square root of the volume, so it's much smaller. So so G is amenable if this quantity is 0, otherwise non-amenable. Okay, so and so the way I think of amenable graphs is I immediately think of ZD, and the way I think of non-amenable graphs is I think of regular trees, and if I need to think about cycles, I think of hyperbolic tessellations. But for most part of the talk, just think about a regular tree. Okay, and that worked fine for me throughout the project. So most of the things that are true for regular trees should be true in general cases. But there are many examples of hyperbolic graphs. Okay, so here's a picture of a hyperbolic graph. This is a nice artwork by Escher. I'm sure many of you know him. Okay, and you can see that the boundary, since it grows very fast, the only way to draw it will be to have like limit points on the boundary, like all throughout the boundary. Okay, so you can't draw it so that on the plane in a nice way so that you fill up the whole plane. But that's okay. But all right. So here's the theorem. So take any bounded degree graph, and omega is this site percolation, and you look at again the sites which are connected to infinity. All right. So if G is amenable, then we already saw almost a proof of this, that the largest Bernoulli you dominate is as parameter 0. And if it's non-amenable, then actually we can prove the strongest possible statement that the invariant the invariant domination that you can do of a Bernoulli, the parameter you can make it go to 1. Okay. So just for contrast, in the proof I gave for the tree, the Bernoulli I dominated, the parameter went to 0 as p went to 1. But actually in the theorem we prove something way stronger. So definitely that proof doesn't work. We need to do something else. But this is what we get. Okay. Any questions about the theorem? This speed will depend on the specific graph, of course. We didn't calculate it, but certainly something could be done on the tree. Yeah, it will depend on percolating probabilities and things like that. Yeah. Any other question? Okay, so the first part is the easy part. I almost gave a proof of this, and the second part is of course the harder part. Okay, so we have some results for the easing model as well, and so we saw definitions in Lucas' talk, in Yuao's talk, and then several talks. But still, let me just quickly define it. It's a probability measure on +1 and -1. So beta is this inverse temperature, and we are going to be looking at sort of this pure limits, so the plus boundary limits. So we are going to take a sequence of exhaustions of my graph. So my graph is now general, it's not ZD or things like that, but still this limit does exist. It's a consequence of monotonicity, and in the end you get these sort of Gibbs measures satisfying DLR equations for me, which I denote by mu beta plus. And the questions we are going to ask, does this, if beta is very low, okay, so it's known that there is some critical temperature such that if beta is lower than that, so beta is inverse temperature, so at high temperature there is no magnetization, so it's kind of all mixed up, the red and blue. If beta is large, then there is some magnetization, so it's either red or blue, or actually with plus boundary conditions it's going to be this, it's plus all through, like a big C of plus. And the question we are going to ask is in this side, if beta is very low with plus boundary conditions, so you see a sea of pluses, can you dominate a Bernoulli percolation with a very high density? Okay. Okay, so that's the question, and here is a theorem which is of similar flavor. If G is amenable, then the largest Bernoulli you can dominate will go to 0. If it's non-amenable, then the largest Bernoulli you dominate will go to 1. Okay, a very similar type of theorem. So that's the theorem about easing. Any questions about the theorem? Yes. Yeah, think of 1 and 0, and yeah, plus is 1, minus is 0 for me, and you can define order. Close to the critical temperature, you will dominate some Bernoulli. So you will always dominate some positive Bernoulli. You see here it's not exactly 0. It's because of the nature of the model somehow. I mean the percolation set we defined, that was not Markov in any sense in which easing is. So somehow that looked maybe more innocent than easing model, but somehow I feel that that's a much harder model to study than the easing model. Easing model has many nice properties. But anyway, it will dominate some positive Bernoulli. You can probably calculate or estimate that, but since it's some positive number and we didn't really think it's that interesting to calculate the exact value. Yeah.
Is this the relation with disagreement percolation?
So the technique I'm going to talk about soon. So disagreement percolation is one way to go about it, but since we are looking for here in this part, we're looking for invariant things, it's a bit harder to do that. So we went through this sort of exploration and trying to do things, but if you want to make things invariant, it's not so easy. That's why I'll talk about it at the end. Yeah.
You can do this for any temperature, then you will show that when it increases, it gets closest to 1, or you need at some point to take the limit on the temperature.
You mean in the amenable setup?
Yeah.
Yeah. So for any temperature, it will dominate. I mean, P of this is some positive number, but the thing is that as beta goes to infinity, this will tend to 0, and if beta goes to infinity, here it will tend to 1. That's the dichotomy. Okay. Anything? Any other question about the theorem? Okay. All right. So here's another theorem. The next we ask. We started to dominate Bernoulli percolation, but why just limit ourselves to Bernoulli? Suppose I'm given two Isings, okay? One with temperature beta 1 and another with temperature beta 2, okay? And beta 1, let's say, is bigger than beta 2. And the question is, does one dominate the other, right? And, in the picture, it seems like you dominate because the pluses get bigger and so on, the same kind of ideas. And you have a similar theorem. So if G is amenable, these two are not stochastically comparable, meaning you can't couple one way or the other, okay? But if it's non-amenable, then what you expected or intuitively expect at the beginning is true, that mu beta 1 plus will dominate mu beta 2 plus. So this theorem answers a question of Liggett type. The previous theorems also answer some question due to Liggett type. Okay, so that's the end of the first part. Now let me move on to the second topic, which was kind of the motivation of this work, and this involves something called a factor of IID. Right. Okay, so what is a factor of IID? So if I'm given a stochastic process, the question I'm going to ask is that can you write it as a measurable function of an IID process? Okay, so imagine Ising model. Okay, that's kind of the go-to model for us. You're given an Ising model, can you write it? So imagine you have an IID random variable attached to every vertex of your graph. Can you write the Ising model as a measurable function of those IID random variables? Okay, and not only that, we are going to also ask for some invariance of this function. We want this function to be automorphism equivariant, which kind of means that if you apply an automorphism, this function will commute with it. Okay, so in plain words, this function is not going to look at the location of the graph, but it will look locally around you, and it will look at the geometry of the graph and the IID variables and throw out a plus or minus, and this and if you just look at all of these outcomes, then you get the Ising model. Okay, that's the thing we want to construct, right? So this has some algorithmic motivations, particularly in finite graphs. People want to do it for obvious reasons. But for us, it's more purely a probability theoretic question, I would say. We are just asking if there exists such a thing in the infinite setup. Okay, there are ways to go to the finite setup from the infinite setup, but I'm not going to talk about that. Okay, and then you can ask for even more. If this function, so you look around you, and if you just need to look at some finite neighborhood, and that's all you need to output your x, then we say it's a finitary factor of IID. Note that this finite thing, this finite radius, may not be something deterministic. It could be random. Okay, so you might look at the values, and depending on the values, you might decide to look a bit further, but you must, with probability 1, stop at some point. It's like a stopping time type of random variable, this R. You can think about it like this, but in a graph spatial setting. Okay, so that's a finitary factor of IID. Okay, and so here's an example I like to start with, because I think this is what helped me understand these ideas quite well. So again, take a Bernoulli bond percolation. Okay, so imagine Z2. Okay, and then let's say I do the following. For every component, I toss a coin independently and color it 1 or -1, let's say with probability half. Okay, so that gives me a bunch of 1s and -1s, and let's say now you forget the Bernoulli, the edges that were open, and the question is this a factor of IID? Okay, and the easiest case is if all the components are finite. So in Z2, if P is strictly less than PC. If all the components are finite, then indeed the answer is yes. And let me explain to you the factor map in words. You simply look around you and look around you until the Bernoulli. So you sample a Bernoulli percolation, because that's of course a factor of IID, because it's just IID. Okay, and then you look around you as a function of those Bernoulli variables, and you stop when the cluster stops, and you will stop almost surely because all the components are finite. It might be very, very large, but you will stop for sure because P is less than PC. And once you stop, you select one of the vertices in your component uniformly at random, and the way to do it as a factor is you attach a bunch of uniform variables on the vertices and pick the maximum one. That's just one way to pick a uniform variable, a uniform element from a finite set. And depending on that uniform variable, you can color the component 1 or minus 1. So let's say if the uniform is less than half, you color it 1. If it's bigger than half, then you color it minus 1. Okay, and so this is the explicit function which tells you how to generate this stochastic process, which I sort of defined. It's a completely made up process, but I think it highlights the ideas quite well. Okay, so in here the answer is yes. Okay, that things get more complicated if there are infinite components. So suppose there is a unique infinite component, just like in ZD. Okay, is it a factor of IID? And you quickly find that the answer is no. That's simply because if you're a factor of IID, since Kolmogorov 0-1 law tells you that the tail sigma algebra is trivial for IID random variables, that's also true for factors of IID. The process, if it's a factor of IID, the process in particular has to be ergodic. Okay, but if you have an infinite component and you color it 1 or minus 1, then you have a translation invariant event, which is simply that you have a giant infinite cluster of +1, and that occurs with probability half. So it's not ergodic, and so therefore it cannot be a factor of IID. Okay, so already you see there is a big difference between depending on how you construct the thing, whether it's a factor of IID or not. Does this make sense? Okay. Okay. Now, what if there are infinitely many infinite components? This is not something I made up. That this does happen. For example, on a tree, if you do percolation above the critical value, then you are going to get infinitely many infinite components. Okay. So in that setup, this argument doesn't really work, because you're going to get infinitely many infinite +1 clusters and infinitely many infinite -1 clusters. So you can't really come up with an invariant event very easily. And indeed, the answer in this case is quite hard. In fact, it's one of the open questions in this area. It's not written in this setup in this language, but it's almost equivalent. So here is a theorem due to Sly. It says that if you look at the free boundary Ising model, so you take the Ising model but don't put any boundary condition on a regular tree, okay, the simplest setup you can imagine, and let the tree go to infinity, you get this free boundary model. This is not a factor of IID at very low temperature. Okay, so this infinitely many infinite clusters somehow plays a role, and it's an open question whether at intermediate temperatures is it a factor of IID. There was a recent breakthrough for high degrees by Sly, Nam, and Zhang. Okay, so this is hard. So let's make things a bit easier. Suppose we color every infinite cluster deterministically plus. So there is no randomness in the coloring of the infinite cluster. Okay, so is this a factor of IID? And here actually the answer is yes, because if you want things to be a factor of IID, you just look around you, and if the cluster is finite, the bond percolation cluster is finite, then okay, then you do the same thing that we did when all the clusters were finite. But if you go very far and you still haven't finished your cluster, that means with kind of high probability you are in an infinite cluster, and then you color it plus, and that gives you almost a map which works like at almost all vertices. And since I'm not asking for something finitary, this indeed will get you, if you take a limit in a suitable sense, then this will indeed get you the Ising or this model as a factor of IID, but it will not be finitary. Okay, so that's the next question. is this a finitary factor? So you have infinite components, and it's the immediate thing will not work, because no matter how far you look, you're not sure if the cluster is finished or not. It might be a giant finite cluster, so you don't know just by looking in your neighborhood. So that's the problem here. You kind of need to look all the way to infinity to make sure that this is an infinite cluster, and then you can color it plus. Okay, so this is the question we will tackle, and this was the sort of the motivation, because this free boundary Ising model is a fascinating question in my point of view. It's such a simple model. It's just an Ising model on a tree. It's a Markov chain. It's a tree-valued Markov chain, and still here is a question which is open for such a long time. Okay, so we asked, okay, so if you take the plus model, it's a finite factor of ID, but what if is this a finitary factor? I mean, at very low temperature, can it be not a finitary factor? Okay. And again, we found that the answer depends on the geometry of the graph. Okay, so here is a proof which will look very similar to the percolation thing that I talked about. So this goes back to Vandenberg and Steiff. If you take a low temperature Ising on an amenable graph, so think ZD, then it is not a finitary factor of IID. It is a factor of IID because of the same argument which I just outlined. You just go very, very far and you color things plus if you haven't finished your cluster, but it's not a finitary factor of IID. And here is a proof. So if it was a finitary factor, then there is a sort of a large deviation principle that will kick in, right? If you have a bunch of IID random variables which are plus with high probability, let's say, then if you ask the probability that a constant proportion of those variables are minus, then that probability is exponentially small in the number of variables. So the same thing will be true if it's a finitary factor of IID. It's not really IID, but it's a finitary factor, and one can show that if you ask for the probability for the plus measure, so you have a sea of pluses, what is the probability that you find a lot of minuses in a box? Okay, so this C, if it's large enough, then you can make sure that this probability is actually exponentially small in the volume of the box. Okay, so that's one consequence if it was a finitary factor of IID. All right, but then we'll play the same game. We will tweak the boundary of the box, and if you have an Ising model, changing a vertex to plus and minus only has a finite cost. Right. So if you have a finite box, if you change the boundary, all the boundary vertices to minus, that has this cost, which is exponential in the size of the boundary of the box. But once you do that, since it's a low temperature Ising model, and if you have a minus boundary on your box, everything will be minus for free with high probability, with positive probability, right? So actually, one can show that, this argument will tell you that this probability is actually exponentially, at least exponent e to the minus c times the size of the boundary. Okay, and these two things can't be true at the same time. Okay, it can't be at most exponentially small in the volume, and it can't be at least exponentially small in the boundary once the boundary is much smaller than the volume. That's right. You need a notion of finite energy, so you need to be able to flip things with positive cost. So that's true for the Ising model. But once you have that and you're on an amenable graph, it does work. Yeah, it's a very general argument. Okay, but you immediately see that this won't immediately work if the boundary is of the size of the volume. Then this is not true. So there is no contradiction. So the question still remains, on a tree at very low temperature, is it a finitary factor? Okay, and so here's a theorem. So if you have a non-amenable, quasi-transitive graph, then if beta is sufficiently large, then your Ising model is indeed a finitary factor of an IID process. So the answer is indeed yes. So this again gives you a dichotomy, right? So for the amenable setup, it was not, and so again, you can ask the same question for this percolation set that we talked about. Again, on a non-amenable quasi-transitive graph, you can ask, is it a factor or finitary factor? And indeed, it is a finitary factor of ID process as long as p is very close to 1. So one thing I'd like to point out that these temperatures are very large and p is very close to 1. So this is again one of those results which is true in the perturbative setup. We had many of those yesterday. And we tried quite hard for, in this setup, even in the simplest case for a regular tree, to push this result all the way to criticality. We kind of believe that it's true as long as beta is bigger than beta c, but we don't have a proof even in the simplest case of a regular tree. Okay, so it's all perturbative, all these results, unfortunately. Okay, so that's one of the open questions. Okay, any question about the theorem? This I'm not aware of, but
that generates the actual configuration in the window with the right probability.
Yes, and so if you have such an algorithm, then and if this algorithm doesn't, I mean, it's invariant with respect to the location of the graph, then indeed that should give you finitary factor. That's exactly the definition of a finitary factor. So once you have that, then indeed you have it. Yeah, we don't know if there is such an algorithm on a regular tree if beta is bigger than beta c but close to beta c. Yeah, exactly. All right, so let me tell you a little bit about the proofs. Okay, so how do you prove stochastic domination? And let's ask, how do you prove invariant domination, right? So we gave an idea for sort of going one by one and trying to dominate the conditional probabilities one by one. But here is a way to do it sort of together at the same time. So if suppose you have two random samples from probability measures on 0, 1 to the v, and suppose this condition hold, which is known as Holly's condition. So you condition on the values outside a vertex v, okay, and okay, so you have two samples, xi and xi prime, outside a vertex v, and suppose xi is bigger than xi prime. Okay, and if you have this conditional probability bigger for every such pair xi and xi prime, then it does follow that xi stochastically dominates xi prime. Okay, so it's a very strong condition. It has to hold for every pair, such pair xi and xi prime. Okay, and let me also give you a flavor of the proof because I kind of like it very much. Simply, you start with two configurations, one way above the other, and you run a Glauber dynamics, and Glauber dynamics is simply you update a vertex given the rest, and you sort of do it together for both, maintaining the ordering at every vertex. So you start with two configurations, one above the other, and you update everything, maintaining the ordering. Now on a finite graph, so this is for a finite set. So on a finite graph, at some point, it's a Markov chain, and if it's irreducible, periodic, and so on, it will converge to the stationary distribution, and the stationary distribution has to be the right distribution for xi and xi prime. So in the limit, you will get the coupling, right? In the limit, you will get the marginals of the right things, and you maintain the ordering as you do it. Okay. So one of the challenges to prove stochastic domination, for example, in infinite graph, is to come up with a version of this in the infinite setting. Now here, the way you do it is you pick a vertex at random, you update, you pick a vertex at random, you update, and so on. But in an infinite graph, this uniform choice of a vertex doesn't make sense, so you kind of need to do something else, and that's one of the challenges, okay, to prove domination, for example, on an infinite graph. Okay. But Holly is too strong somehow. So here is an example which tells you sort of how bad Holly is in certain situations. Suppose you have these this pair of random variables, which is 1, 1 with some probability and 0, 0 with some other probability, and those are the only two values it takes. Now clearly, this pair xu xv, this will dominate a Bernoulli with probability p. Okay. this you can just simply check, because the Bernoulli is 0, 0 with probability 1 minus p square, and you put everything else on the highest possible value, so it will dominate a Bernoulli p. But if you look at Holly, once you know one of the vertices is 0, then XU is unfortunately 0 with probability 1. You cannot be a 1, 0. Okay, so Holly doesn't work. And sort of a similar thing happens in our models, right? So, you know, if we look at this percolation set, if you're surrounded by zeros, that means the thing inside cannot escape to infinity, so you're 0 with probability 1, which is something that you don't want if you want to dominate a high density Bernoulli. And similarly for easing, even if the temperature is very low, if you're surrounded by -1, then with high probability the vertex is -1. It's ferromagnetic easing, right? So it kind of goes against what we want, and if you try to apply Holly directly, you can't get a domination even in a finite graph. Okay. So what's the idea? The idea is to dilute the process in a certain way, and the way, I mean, the simplest way you can think of diluting it, and by dilution I mean you start with the easing model. Okay, the Holly is very rigid because if you're surrounded by minuses, then you're minus with very high probability. But what I want to do is I want to look at some of the pluses, and with very small probability I'll flip the sign. Okay, so this will sort of make some of the pluses minuses. The minuses will remain minus, but the set of minuses sort of increase. Okay, so you get a more complicated model if you do this. If you look at the configuration that you get in the end, it's not easing. It will have long range correlations. However, the issue with Holly will go away, because if you know you're surrounded by minuses, maybe that minus came from a plus. Actually, it came from a plus with a high probability, kind of. Right? So, okay, so you independently for every minus, for every plus, you keep it with some probability and you flip it with some probability. So that's like diluting the pluses a little bit. So, you know, immediately you see that the problem is not immediate. There's some calculation that you need to do. And in this calculation, if the theorem is right, non-amenability has to enter at some point. Okay, and the hope is that this diluted process actually will dominate a Bernoulli for a very large parameter. And if it does, then the original process will also dominate it, because we made the process lower by diluting it. So that's the hope. So we want to apply Holly with this for this diluted process. Okay, so but you know, this whatever the proof is, it cannot work for ZD, because in ZD the theorem is false. Okay, that's the situation. So let's try to compute what the law of my process is. What the law of the actual process is once you condition on the diluted guy. So tau is the diluted guy, and this is a base calculation. Okay, so let's given the calculation to you, but let's look at this bullet point. If you're given the diluted process, then wherever the diluted process is plus, the easing is of course plus, but wherever it is minus, it's distributed as an easing model with plus boundary condition, but there is a negative magnetic field which will come into those vertices with this intensity. Okay, it's a base calculation that you can do. So what do you get in the end? The conditional law is a situation where you have lots of pluses, and in the holes left over by the pluses, you have an easing model with plus boundary condition but negative magnetic field. Okay, that's the setup. And okay, so once you have this, then if you want the probability that the spin is plus given tau, then by monotonicity of easing essentially, because this is another easing model with magnetic field, it's sort of the lowest when everything is minus, right? So imagine the diluted guy is all minus. What's the probability that a vertex is plus? Okay, this is the calculation we'll do, and once we do it, we are done, because everything else will be even bigger. Okay, so this is the worst possible thing that we can get. And now here it's basically a Parallels argument. We saw many versions of that yesterday in Lucas's talk, in Joao's talk, and this is so when you have, so CV is the component of minus containing V. So if once you flip this minuses to plus, you gain this sort of boundary effect, but you lose this thing because of the negative magnetic field. Okay, that's essentially what it is. But now we know that the boundary is constant times the bulk, right? So now if you go through the usual way of doing parallels, you get this probability, this sum. This constant is the number of components of size n, that's some exponentially large in n. Now if you tune your p in the right way, so fix your beta large, h is positive, so this one is there. Now if you fix your p in the right way, so it's small, but it cannot be too small. It has to be, it has to beat this exponential, I mean it has to still not kill this e to the minus 2 beta, but if you tune it right enough, then you can see that this summation is less than epsilon. So overall what we get is that the probability that you get a minus given everything is minus is very small, which means that the probability of plus is very high, okay? And the non-amenability enters the calculation in this way. And the way to think about this is that if the magnetic field is negative, but not too negative, then the boundary, since it's large, still wins. And the dilution helped us applying Holly. Okay, that's the way I think about this. Okay, so that's sort of the so this is kind of the first calculations that we did. Of course, you need to tweak things to get invariant domination and everything, but this is sort of the core idea of when non-amenability comes in. Okay, so this is it. Now you can try to do the same thing for the infinite clusters of Bernoulli, but as I mentioned, the infinite clusters of Bernoulli, in my opinion, is a harder problem to analyze than Ising, because you don't have this Markov property, and this monotonicity and all these inequalities that we have for Ising is not available for Bernoulli. So it was quite a hard work to get this right for this sort of this weird model of infinite clusters of Bernoulli. And in a sense, the finitary factor result for infinite clusters of Bernoulli, in my opinion, is a much more strange result, because somehow you are bringing in information from infinity at every vertex, but still you can sample it in a finitary way. You look at a finitary window and you can sample it. So that that somehow is not counterintuitive in my opinion, but still you can do it as long as the graph is non-amenable. Okay, so how do you go to a factor of ID? Let me stick to Ising. And here is a wrong proof. This is what we tried to do at the beginning. So dilute sigma to get tau, and once you have tau, which is the dilute guy, then we know that the Ising will dominate this dilute guy, which dominates this Bernoulli. So you have three processes sort of living together, ordered, and this is a high density Bernoulli. And that's the idea, because Bernoulli percolation is of course a factor of ID. So you first sample that, okay? So you got your eta, and if this eta is large enough so that what you're left with is some finite holes, then maybe in those finite holes you can compute this conditional law of sigma given eta or maybe tau given eta in a finitary way to get your algorithm. So the algorithm at its heart is like you sample a Bernoulli, you break your graph into finite holes, that's where the p close to 1 comes in, and once you have your finite holes, everything becomes finitary from the algorithmic perspective. Okay, that was the idea. Okay, so you sample first and then you get the holes, and maybe you can get the finitary vectors. But the issue that we could not overcome, this seemed like a simple thing that we should be able to do, it breaks up into finite things, but if you want this coupling to be invariant, which you must have if you want finitary factor or even invariant domination, constructing this coupling in an invariant way was hard. The issue is that you can sort of do this dynamics approach and couple them invariantly, but if you do this dynamics approach, then you want the holes that are left over by the eta, it's not clear that they're independent, because the information from the holes might seep through the dynamics. Okay, and then you can say, okay, I'll not do the dynamics, I'll sort of explore from the outside and try to couple things maybe in an invariant way. I don't know, some way that keeps the independence, but that's all. But we couldn't get the invariance to work for that. So for a long time we tried this, and it didn't work. So in the end we had to directly prove it. Okay, and the way to directly prove these things is to sort of look at the dynamics in space-time. I don't have too much time to explain this, but the point is that you start, so you want to construct this function, right? So you start at the top where everything is unknown. So cross means unknown. I don't know what the value is, and I want to know what the value is. Now what I do know, so let's say I want to sample the dilute guy, and I know that it dominates a Bernoulli. So given no matter what I see on the outside, the probability that my guy is a +1 is very high. That I do know. So I will try to update it, and with some very decent probability independent of everything else, I'll see a 1, and those are these bullet points here, and this axis is the time. So this is a picture drawn in space time, and the punchline is that you can translate everything to a percolation question in the space time, and the point is that if you want to know the value at some point at the bottom, then you sort of go up, and if this, so imagine this is like water percolating through from top to bottom, and if the water reaches the bottom, then I don't know the value, and if it does not reach the bottom, then I do know the value. So if you translate the questions of finite factor through some arguments in this sort of setup, then that's the question we need to answer, and in the end we get a percolation question on this sort of, it's not a graph, but in this sort of setup we want to know what is the probability that you're sort of surrounded by a shell of plus 1 bullet points, and imagine these +1 bullet points are with very high probability, very high density percolation. So once you write this in this setup, then you can prove that you're surrounded by these sort of walls with high probability. Okay, that's in a very in a small nutshell, this is the idea. All right, so I'm going to wrap this up soon. So how 5 minutes, 2 minutes? Oh, it's already 7 minutes over time. Okay, so I'll stop soon. But let me just quickly mention just one thing, and then I'll stop. Promise. So for the two comparing the two easing, dilution with independent Bernoulli percolation does not work, because if beta 1 and beta 2 are too close, then the dilution also needs to be small. But we already saw that the dilution needs to be a little bit strong so that the non-amenability kicks in. Okay, so in roughly that's the reason why independent Bernoulli dilution doesn't work. So here we actually need to employ ideas from this theory of lattice gases, which I guess is related to what you were talking about yesterday. So we don't do dilution using independent percolation, but we sort of do it using a probability measure which you can get from the theory of lattice gases using this so-called Lovász local lemma. Okay, so it's a dependent percolation model, but somehow that needs to be employed in order to make sure that this domination of the two easings work. Okay, so let me just quickly go through. So here's some questions, and here's, in my opinion, the most interesting open question of all. Is the plus easing model a finite factor of IID? Let's say for a regular tree for temperature close to the critical temperature. And here I have a toy question which should give us some ideas on how to attack this problem. So let me not explain the toy question and leave it up here, and let me stop here. So thank you very much for your attention.
I have a comment. So it looks to me that in at least in the statistical mechanical model, things get easier when you have uniqueness.
Yes.
But of course, the case is not unique. So maybe you can turn around the question and say, in general, whether you can classify classes of maximum classes that can be dominated, but they cannot dominate everything. Typical flat face on one side and the minus face on the other side. You cannot dominate both. It would be an alternative way to characterize.
Yes. So there are theorems like this, not on the domination side, but on the factor side. So if you have models which are monotone in a certain sense, and there is a unique Gibbs measure with some sort of Markov property, then Okay, so then the theorem is that it is a finite Theory factor if and only if there is unique Gibbs measure. Okay, so the theorem, the motivation was to do it for the random cluster model. So you need monotonicity and you need like a ceiling and a floor configuration. It can't be like the 6 vertex height function where it's infinite. You need like it has to be sandwiched between two. It has to be monotone and there has to be a unique Gibbs. So then it's a finite Theory factor if and only if there's a unique Gibbs measure. So there are theorems like that. But on the domination side, there should be some theorems like that. But yeah. So at the moment the results are all like perturbative, so either the temperature is going to infinity or so on. But indeed, when we saw that near criticality, this is one of the open questions, right? I mean, if this question has an answer, then this will sort of say that the Ising model is a finite Theory. Well, on a non-amenable graph, it will be a finite Theory factor. Okay, here it's not going to be a characterization because if beta is less than beta c, we already know it's a finite Theory factor. So it's a finite Theory. There is no phase transition in terms of finite Theory factor on a non-amenable graph if there is an answer for this. But on an amenable graph, indeed, it's not a finite Theory factor if it's low temperature, and it is a finite Theory factor if it's high temperature or critical temperature. So that's known. So there is some results like that. So indeed, this is one way to characterize phase transition as well. So that's one of the things that you can do, indeed.
No more questions?
Okay. Oh.
Usual definition of the Hamiltonian, which is the sum of the potentials with the boundary condition that always considering to be denoted by omega, and sigma is the configuration inside of the box lambda. And I'm always considering the potential to be absolutely summable. So this is the notation. This is the condition that we're always considering during this talk. Okay, so this condition is at least we can do some computations inside. One type of consequence that we can do that we have asking this absolutely summable potential is that we can use the Dobrushin uniqueness region at sufficiently high temperature. We know that there is no phase transition. They have uniqueness when the infinite volume Gibbs measures. All right, so these are the settings of the potential. So with them, it is enough to define the measure, the Gibbs measure. Usual Gibbs measure, again, we have a few people here to already define the Gibbs measure, is the probability measure which follows the law, which is the exponential of the negative beta times Hamiltonian. Beta, the usual beta, which is the inverse temperature, always positive. Okay? C is just a notation for the partition function. Once that we have the Gibbs measure, so let's start and talk about the question that we want. We want to talk about the central limits and local CLT, the local central limit theorem. For that, even for the classical case, for the IID, we should ask a little bit more conditions for the state space. So let's consider our E, the set of the state space, set of the spins, to be lattice distributed. By definition, lattice distributed means that the set is of the form of natural numbers, integers, where it forms an arithmetic progression. That's it. Okay? Since we are asking E to be finite, we are considering arithmetic progression of finite size. Okay? Here, A and H. A is the fixed number, is a fixed integer number. Our H is the common difference. Usually in the textbook, we use R, small r, to denote the ratio of this common difference. Here, because of some settings of some textbook, we are keeping the notation to be H, our common difference. Once that we have this setting, we can see clearly that the spin should be of the form A plus B times H, where the B is the parameter that we are running from two integer numbers, from P to Q, two fixed integer numbers. That's it, okay? This is the state space. Okay, so once that we have the lattice distributed state space, let me quickly state the classical, the baby version of the central limit theorem. So I'm quite sure that almost everyone here know the statement of the CLT. So let's go very quickly with the statements. So we have a sequence of IID random variables. Let me use here xi. Okay, a sequence of IID real random variables. Let me just do some renormalization. We should have a mean 0 and variance 1. Once that we have all these settings, if we denote Sn to be the sum of the first n of these random variables, we have the central limit theorem, which basically says that the sum Sn converges in distribution to the Gaussian. That's it. Let me give you a little bit teaser of what we are going to talk about today. So imagine that this xi is the spin of the Gibbs measure. So of course we cannot apply this result because we are asking the xi to be independent. And of course in the system like as a model, Potts model, for example, it's highly dependent. So we cannot really apply these results. So one type of question is it possible to define a new notion of CLT for the central limit theorem if you consider the law following the Gibbs measure? Again, we are talking about central limit and local CLT. So let me quickly talk about the classical local CLT as well. So this is the of the conditions. Note that here it's really important to ask that we are talking about the random variables to be lattice distributed. And in that case, basically local CLT says that the density, so here just since it's finite point-wise, it converts to the Gaussian density. Very easy. This is the local CLT. Okay. Again, note that the conditions here, we are assuming the random variable to be IID, or in particular, it is independent. We cannot really apply these results for the easy mode, for the usual models in the statistical mechanics. We have a lot of dependence of the spins. Okay. Once that we have this two in the classical way, now the next question, as I'm always repeating, how to define, how to give the new notion of the CLT and the local central limit theorem for the statistical mechanics model for general potentials. Of course, we have to define what SK means in that case. So since we are talking about spins on the lattice ZD, so here we are always considering our finite set, our box lambda of size 2k, to be the usual box, negative k to k, to the power d, the usual box, okay, of in the ZD. Remember that we are always keeping the state space to be lattice distributed. And now we can define the sum Sk to be the sum of the spins running over all sides x to be inside of the box lambda k. So this is the usual, this is what we are calling about Sk to define the CLT. I'm using this bar on the top of Sk after we scale properly to make it mean 0 variance 1. From this talk, I'm using dk to denote the variance. Whenever I'm using dk during the talk, I will always call as variance. Okay? So we are talking about square root of dk to be the standard deviation. Okay. Yes? Huh?
E like a continuous?
Doesn't have to continue. No, so here I'm talking about b to be integer. Sorry, yes, it's a good point. So b is integer. So we are talking p, q are integer numbers. B is running from all of the possible integer from p to q. So it's finite sets. All right, so now we are able to define what CLT means for the Gibbs measures. We are considering sequence of the Gibbs measure, that's here, where the boundary condition can be very arbitrary. It can be any sequence omega k. And know that we are increasing over the boxes, lambda k. And we say that CLT holds for the Gibbs measure, for the sequence of the Gibbs measure, if all of these three conditions holds. So basically what's happening here, the first two conditions basically says that the variance should increase at the same speed as the box, at the size of the box, the volume. Dk and alpha k. In fact, depend on omega, in fact, these parts. You're right. It's alpha dependence, it's omega k dependence. Once that we have alpha this condition, should be properly okay, should be fine. So this limit basically saying that the limit exists and should be positive. Or in other case, you can also simplify. You can also consider the boundary condition to be fixed. It's also okay. Since we have this, usually in the conditions, the I have the experience defining these definitions. They probably implicitly mention that alpha should be uniform in some sense. It's a good, actually, it's a good point what you're talking about here. Should be just a constant, independent of the omega k. It's a good point. Yeah, thank you. Good point. Last item, the third item is basically CLT. So just a weird way, just setting by using the Gibbs measure, but you know that we are talking about SK with the right scaling, converge distribution to the Gaussian. Okay, so now we have our CLT here. The same thing happens for the local CLT. So first two items, exactly the same conditions, and the third item, although this looks very complicated, is exactly the same in local CLT that I already explained before the classical definition. So just a copy paste by using the different settings by using sequence of Gibbs measure. That's it. Okay, so this is enough to define CLT and local CLT. Now we have the following question: for which models, for which potential, we do have the central limit theorem? For which model we do have the local central limit theorem? Let me give a list of the results such that we do have conditions so that the sequence of the Gibbs measure does satisfy CLT. So we have here just an epsilon list because the results about the CLT is huge. And I've just talked about one that's basically related to the sequence of the Gibbs measure or percolations. But among all of these items that I listed here, I would like to take a look, to focus on the result from the Chuck Newman, where he proved CLT if you have a model that does satisfy the FKD conditions and the susceptibility is finite. Okay. The main difference between these two items that after 3 years, Newman just said that we have an extended version, generalized version. The generalized extended version basically says that events that you want to consider to analyze your CLT doesn't have to be monotonic. Okay, so there is you can drop that condition, adding more families of the potentials. So this is all the result. There are some other results about the percolation for Cox limits, some about the associated random variables percolation model, and there's one that's almost recently, Barbosa, Yantai, Kovchakov, Yishu, proved the Newman central limit theorem via a new method that's called the Stice method. Okay. So, for example, for the Newman case here, you can apply the first one. You can apply for the Ising model, for example, the nearest neighbor Ising model off of the critical temperature, where it's ferromagnetic. For sure, we know that FKG inequality is satisfied, and the susceptibility is finite, for example. So in this case, we know that it does satisfy the CLT. Okay. All right, so this is the list of the central limit theorem. So how about the local CLT? Of the result that I know, so as far as I know, of the result that we have about the local CLT is about a statement about the implication where you assume that you have CLT, then you can prove the local CLT. So here is a list of this type of results. First result by Del Grosso, who proved that if you add some extra condition, we can show that for the short range translation invariant potential with some constraints. I'm not going to give these constraints, too technical. Assuming that the state space is finite, then we do have CLT implies local CLT. It's okay to avoid to just miss all the condition of these constraints, because later on Dobruch and Tiros just say that any short range potential works. Doesn't have to assume any new constraints to have this implication CLT implies local CLT. So it's a very powerful result considering the short range translation invariant potentials. So there are some other rooms here that you can improve. For example, this Campanino, Del Grosso, Tirozzi prove it for the short range, but instead of considering the state space to be finite, we can consider the state space to be the integer numbers. Actually, even inside of this paper, they can also consider the state space to be continuous, to be the real numbers, for example. Know that they have to ask the potential to be exponential mixing. So if we have to consider a strong condition so that we have space, the potential should satisfy some CLT behavior. All right, and then know that all of these three items we are always focusing on the short range potential. So how about the long range? What's happened with the long range potentials? There is a result from Campanino, Capocaccia, Tirozzi, who proved that statement CLT implies local CLT for the long range translation invariant potential, satisfying some constraints. Next slide, I'm going to give that constraint, but note that also we went back so that the state space is finite. Something very important here, although I'm quite sure that everyone already realized, be careful with all of these conditions. All of the results proves, assuming that CLT holds, then we can conclude local CLT. So we are not basically saying that local CLT always holds. We need to add more conditions so that the CLT should be satisfied. All right, so now let's state the result from Campanino, Capocaccia, and Tirozzi. Let's consider a very specific type of potential. Ising type is a Jx minus y translation invariant that we will have the dependence on the distance, sigma x, sigma y. So we have here the settings that kind of Potts type or Ising type, and Campanino, Capocaccia, Tirozzi states that if you have a potential satisfying that condition, the sum of all the interaction in the square root is finite. If this series converts, then CLT implies local CLT. So this is their main results. So this is very nice because they are basically considering a family of models that are long range. Now, in particular, short range should satisfy this. So this also includes all of the possible short range models as well. All right, so it's a very interesting result. So once that we have a general result like this, let's try to plug one specific model. So one of the models that actually Lucas and João presented a lot yesterday is what we call the long-range easy model. So let's see what's happening if you plug the long-range model here. 1 minute, I know that everyone already knows that the Hamiltonian of the long-range model, but let me just repeat here. We are fixing to be one-dimensional, so the lattice Z. Okay? Different than what Lucas talked about in the ZD. Here we are focused on Z. The state space is Z in type, so -1 and 1. The Hamiltonian is the long range, so we have here the interaction depend on the distance, and the formula of the interaction, the expression of the interaction is polynomially decaying with some power. But here I'm calling 2 minus alpha, where alpha runs from 0 to 1, including 0, excluding 1. So this is the long-range easy model. Okay? We are considering exactly that interval for alpha because we are in the regime that it does have a phase transition at low temperatures. Okay. Once that we have these settings, let me give a very short historical part of this result. So actually, again, this model is extremely rich. There are a lot of results related to the long-range easy model. And here I'm just focusing on the phase diagram regime. Do you have a question?
Do you need phase transition for safety?
Don't have to. You're going to see. We don't really have to. We don't really have to. But it's a good point. You're going to see in the few slides the reason we are talking about alpha between 0 to 1. But it's not that necessary, actually. So here we have all of the 4 items related to the phase diagram. So first result by Dyson, who proved the phase transition compared with the hierarchical model when alpha between 0 to 1. Note that we are not considering 0. 0 was proved by Frolix and Spencer by using contour arguments. Okay. About the critical temperature, we have a result by Eisenman, Chase, Newman for alpha equal to 0. Just to make sure alpha equal to 0 means that the decayment is quadratic, okay? So as the power is equal to 2. Here we know that the magnetization is discontinuous at the critical temperature. However, for all of the other alphas from 0 to 1, excluding 0, the magnetization is continuous thanks to the result by Eisenman, Dominic-Copan, and Sidorovicius. So we have of the result here, which basically gives of the complete phase diagram of the long-range easy model, one-dimensional here. Okay. All right, and we have some new results here, so recent results. Basically, Lucas and João gave all of the rich details about all of these the first 2 topics. So this was the first one, Afonso Bissacco, myself, and Handa proved it for the lattice ZD. Here is not one-dimensional, but d-dimensional. Lucas gave a lot of details about that condition of new type of contours, proving phase transition of the long ranges in type for any alpha larger than d, specifically between d and d plus 1, by using what they call the multi-scale argument. And we have here by Lucas, Rodrigo, and João a result that actually João just presented yesterday about this phase transition, the class of ferromagnetic random fields, long-range easy model. Here, still for any d-dimensional, something that João just told me today in the morning, that actually this paper was, you put in the paper on the archive very recently, today, I guess, right? Okay, very good. So you can take a look about that results you can find on archive. And here I'm going to give a small advertisement of one of my recent work with Arnold van Enter, Arnold Leni. So we have results about the metastates of the long-range easy model with random boundary condition. So very roughly speaking, it's not the purpose of this talk, but let me just define metastate in one sentence. Metastate, by definition, is the study of the convergent distribution of the family of all possible convergence of the subsequence of the Gibbs measure when you assume that the boundary condition is random. So you want to see if you have a sequence of the Gibbs measure and the boundary condition is random. Of course, the sequence itself might not converge because we are in the crazy situation when the boundary condition is random. But of course, we are in the compact set, so that for sure there are subsequences that converge. So the question is, okay, so if it converts to some specific infinite volume Gibbs measure. So we can organize to have a class of all of the limits and see what's the density, what's the distribution about all of these classes. And we are going to prove, soon we will put on archive, we are almost finishing the paper, that there is a different formula of the metastates taking alpha between 0.5, half and 1. Okay, so this is all of the result that I want to talk about the long-range easy model. Let's go back to the Campanino-Capocaccia-Tirozzi. So remember the condition of them. So we are talking about the sum, the series over all square roots of the interaction. Okay, so since it's translation invariant, we can just sum over all x. That's not the origin. So the computation here, just plug jx equals to the decay, the power decay. That's x to the power -2 minus alpha, and do some basic computation. You can see quickly here, do some small computation. We can just divide by 2, do some computation here. And here's the point that you can see here, why we are talking about alpha between 0 to 1, although we don't have to. So if we restrict to the region where we do have a phase transition regime, and if you compare with this, if you plug that alpha inside of that series, know that if alpha is between 0 to 1, 1 minus alpha over 2 is between half to 1. So we are in a situation when that series diverges. So this means that we cannot really apply Campanino-Capocaccia-Tirozzi. So first question is, for which alpha can we apply? So if you take alpha to be negative, so for sure this will be situation when the series is finite. But as we know, alpha smaller than 0 is basically saying that the power is larger than 2. We are in the regime, we have this uniqueness, there's no phase transition regime. But okay, we are in the region that we can apply Campanino-Capocaccia-Tirozzi. Here, in the case that it's more non-trivial regime, for the case that we have this alpha to be between 0 to 1, we can't really apply. So it's an issue here, it's a problem. Not really a problem, it's just an example that we cannot apply the results. So we have a room here. We can see that we can have another new result. New problem, that is it possible to prove that CLT implies LLT, so local CLT, for the long-range easy model? What we expect is that the results should be very similar to Dobrusin-Tirozzi. If you just recall, Dobrusin-Tirozzi proves that any short-range model, CLT implies LLT. We also expect the same situation here. We also expect that for any temperature, for any long-range model, doesn't have to be easy, any long-range model, absolutely summable, translation invariants, CLT should satisfy local CLT. So what we proved is that the question is basically, yes, we can prove an extension, partially, so far. So this is our statement. So we proved with the settings that the potential is long range, translation invariants. Long range in the sense that at least we should ask the potentials to be absolutely summable. Assume that one of these two conditions holds. So note that we are not assuming both of them. You choose one, either one or other. The first one is not the fun part. It's basically showing that we can extend Campanino-Capocaccia-Tirozzi results, but replace that specific potential to be any potential translation invariant, that we can just plug any potential, should satisfy this condition. We still have CLT implies local CLT. This is not the fun part. The most interesting part actually is the second item. So forget the first item. Suppose that we have a potential that doesn't satisfy the first condition, but let's assume that the temperature is large enough. We are in a condition where beta is sufficiently small. So in that case, we know that CLT implies local CLT. So my comments about, yes, we can extend is exactly the second part. So we can now plug the long-range easy model, partially because we cannot really prove for any temperature, but only for the sufficiently small beta or sufficiently high temperature. So far, because currently we have a project together with Tongxuan Nguyen and Roberto Fernandez, both from NYU-Shanghai, where we are trying to complete all of the diagram, and also we are trying to find different potential covering with more families, trying to remove some new conditions here. For example, we can just remove this state space to be finite, for example. This is one of our current projects. Okay. All right, that's it. So this is the statement of the results, and the rest of the time, I'm going to give the sketch of the proof of this theorem. The first step, although this looks like a very, it looks like that's it's a lot of computation here, it's very technical, but actually, if you are familiar with the proof of the local central limit theorem, you see that this is actually the natural steps to do. So we have here the first line, that's the expression of the local CLT. Remember that our task is to prove that if you take k going to infinity, then that supremum should go to 0. This is our task. This is the proof, how to prove the local CLT. What do we do? First thing that we do some Fourier inverse to make of this expression, the density to depend on the characteristic function. So of the integrands here that you can see are the characteristic function, where the probability measure is the Gibbs measure. Okay, and then we do some clever plus and minus computation. Note that we just add and subtract this exponential and do some clever triangle inequalities. We get of these 4 integrals. So what should we do now? We have to prove that all of these 4 terms are very small when k is large enough. First thing here, b is a free parameter. We can choose b to be extremely large enough so that the second integral is very small. Now, here is exactly the point when we are using the fact that we are assuming CLT. So thanks to the central limit theorem, we know that this integrand is very small, taking k very large. So the first integral is also very small. What remains is the last 2 integrals that I colored in blue here. So know that the integrands are the same. We have to deal with the characteristic functions, where the probability measure is the Gibbs measure. The main difference between both of them is the range of the integration. So the first one, if, for example, if you divide this one by the square root of the variance, if you divide by the square root of decay outside, we are taking k very large. We are basically in the situation when t, this parameter t, is very close to 0. Okay, you can see this, it's very close to 0. While for this one, we are talking when t is far from 0, okay, larger than delta. Keep in mind here that small, very small, close to 0, far from 0, it's the parameter that we can split both of them is this delta. So delta will appear a lot during the proof. Whenever you see delta, basically is the interval where you are splitting t to be smaller than 0 and far from 0. All right, okay, so now note that in the end, we are going to see that the techniques to prove that both of them are very small are basically the same. We are going to use cluster expansion of high temperature, but we have to deal with different activity functions to prove the convergence and being small for both of them. So first one, let's prove that this third one, we are going to prove both. I'll start proving that this third integral is small, and we finish with the last integral. Let's see how to do it. So something very nice, very thanks to Roberto, who already explained us all the rich details about the cluster expansion at high temperature. Of course, he focused on the quantum, he also talked about the classical. Here you are going to see the application of the classical cluster expansion at high temperatures. First thing that we have to do, now that we have this S bar, just some computations, we can remove the mean. So we have only this, just a technical computation to simplify all of the computations. But the important thing here is that identity. We can show that the characteristic function is a ratio of 2 partition functions. Each of them can be written as a gas expansion, also known as polymer expansion. Okay? So if you remember the Roberto's talk, you'll see that we have a lot of similarities. More than similarity is exactly the same here. But we are going to see that we are talking about a specific type of polymer, this R, where Roberto said gamma here, I'm using R as notation for the polymers. It's also 2-body, have some kind of connectivity. We are going to see all of the explanation in the next slides. I'm just showing here that it is possible to rewrite the partition function by using in the form of the gas expansion. Here, something very important, Roberto also explained it, that we also highlight here. we are talking about here the compatibility of the polymers. I'm using this tilde that I'm going to define later, but in basically, roughly speaking, this means that the supports of two polymers are disjoint. This means that they are compatible. I'm using zeta to denote the activity function. So let's see all of the definitions. Well, I just throw here a lot of letters here. So R, zeta, R tilde. So let's have to define here. So let me spend a little bit of time to explain of the notations. Small thing, be careful here. Although it's written here infinite, actually the sum is finite because we are talking about on the settings on the finite box. Okay, so these are fake series. Actually, the sum is finite. All right, so now let's see. Yes?
So the polymers, they are like subgraphs?
We are going to see here. This is the polymer. So these are the polymers. So we first define let me define the polymer here. So we are going to use this notation P12. So the elements of the polymers are what we call bodies. The small b's are just sets with cardinality 1 or 2. Okay? I'm not going to define the polymer in the formal way, so I'm using the pictographic representation of the polymers. Polymers is basically a set of bodies, a finite set of bodies, which should satisfy some connectivity, should be connected. Connected in this sense, as you can see the picture. What does it mean? If you see here B1, B3, we have some intersections here. So this means that we have a connection between B1, B3 because they have a common element. The intersection is now empty. So B1 is connected to BP because we have a chain of non-intersecting bodies going from B1 until BP. So this means that it's connected. Okay? Note that we are talking about one body, two body. There's a reason why we have to include one body. It's because of the T, because of this complex term that appears on the characteristic function. We are going to see later. And this one, for the body with cardinality 1, to be connected, of course, clearly by the picture, you can see that it should be inside of one of the two body sets. So this means a polymer. This is one of the representation of the polymer at high temperatures. I'm using the notation calligraphic R to denote the set of all possible polymers. You don't need to be really careful with to remember all of them. So, and then this tilde is denoted the support of R. So if you remember the tilde that appears to define the compatibility of two polymers, tilde is basically the support. You take the union of all the possible bonds. So we get a subset in ZD. So this is the body. If to be compatible, the support should be disjoint. All right, so this is the polymer. So now we want to define the activity function. So before that, to define the activity function, it is required to define this probability density function, this P omega x, which is basically, if you take a look, it's very similar to the Gibbs measure, where the Hamiltonian is the boundary energy of one point. So the Hamiltonian here, this small h, is the sum of the potential of the interaction between one x that's inside of the box lambda, interact with all the other points that's outside lambda. So this is what we call boundary energy of one point. Okay? And this is the probability density function. The reason why we are defining this PDF is because when you do the computation to define the activity function, to find the gas expansion, you can express the activity function as a product of some fugacities that I'm using psi here, times the product of this PDF. So the main idea, although after discussing with Roberto in the NYU, it's not really required to do that actually, but it works. In these settings, it basically works. The idea to do this PDF is to see that all of this fugacity doesn't depend on the boundary condition. Basically, that's the reason. Okay. Note that we have two types of fugacities. In general, fugacity should depend on beta and t. So we have two fugacities, depend on one body and two body. So the one body fugacity, know that we are basically taking a Mayer expansion minus 1 plus 1, the usual type of technique to find the gas expansion. And here is the term that appears in the characteristic function. Okay? And you can see clearly that the one body the fugacity of the one body depends on t, but not on beta. While the two-body fugacity depends on beta, but not on t. The expression is basically e to the minus beta times the potential. Okay, so we have to deal with these two types of fugacities. One that's complex, depend on t, one body, another is real, two bodies, and depend on the beta. All right, so we have all of the settings. Now it's clear what the gas expansion is, what the polymer expansion is. Again, thanks to Roberto, we know that automatically doing some combinatorial computation, some algebraic computation, it's clear, it's very easy to reach the cluster expansion. We can show that the gas expansion in the logarithm, the log of the gas expansion, can be written as a series where we have to be careful with this function that we call the truncated function as our Ursel function. I can define here. So this is the cluster expansion, where the definition of the Ursel function is a function that depends of the graph of the incompatible graphs. Okay. Something very important about the cluster expansion. Although formally speaking, we can always compute, we can always do this computation from the gas expansion to reach the cluster expansion, we have to be careful with the convergence. So we need to add extra condition on temperature so that with the series is absolutely convergent. Something that I'm going to use later is that remember that if you take two polymers that are the same, they must be incompatible. I'm going to use this information later as well. This is the result about the absolutely convergence of the cluster expansion. It is possible to prove that taking sufficiently high temperature, large temperature, and the delta, remember the delta that's come from the splitting of the interval of t should be small enough, so both delta, beta small enough, then we can show that the series is absolutely convergent. So no more than that, you can really control the absolute value of the series controlled by increasing at most the size of the box times a constant that is very small, very smaller than 1, very close to 0, taking both delta and beta very close to 0. The result works for every t that is inside of smaller than delta square root of dk. So we are talking about the third integral here. Okay. The proof of the result, I'm not going to give all the detail of the proof, but basically just apply Fernandez-Procat's criterion, for example, to get that result. Once that we have this theorem, now we are able to do off the computation of the characteristic function and see how to deal with the integrands by using the cluster expansion. So remember that the characteristic function is a ratio of the gas expansion. Using cluster expansion, it's an exponential of a difference of series. We can factorize some terms using some identity of the complex number. So we have in the end exponential of a series of the cluster expansion of the real parts, difference of the products of the activity function. That's it. Okay, so basically applying cluster expansion here. What should we do? We have to show that this exponential is small enough, taking k very large. So this means that it's enough to control the real parts. We have this difference here. To control that difference, just apply Taylor's expansion. Apply Taylor. Apply Taylor for until the second order. So the zeroth order just cancels out. It is not hard to do some computation and prove that around t equals 0, the first derivative is exactly equal to 0, so just remove them. It only remains the second derivative, the real part of the second derivative when t is truncated. Be careful here, t is not 0, but some theta between 0 to delta square root of the variance. All right, so here's the start of the computation. So we have to deal with this real part. We have to do computation of the derivatives. There's no other way. We have to make our hands dirty. We have to derive twice this product and do some computation. So remember, the idea here, let's go back here, just show you the following. Remember that to show that the integrand is very small, basically we have to prove that this real part increase negatively, so the dominant term is a negative term and should go negatively large in the same size as the size of the box. How to do that? So here are the main specific points where we can split which term is dominant, which term is not. The dominant term are all of the incompatible contours with one body only. That's it. So what we are doing here, we are just splitting the series into 4 parts. Okay? Splitting the series into 4 parts. The first term is only n equals to 1, only one polymer, only one body. This one, 2 polymers, both of them same body, same Y. Splitting off the possible n bodies and the rest. Just put all the others in the last exponential. It is possible from here. I'm not going to do all the computation because it's a lot of technical computation. I'll skip all of them. I'm going to give the final results. But the important stuff here is that the dominant term, the one that gives the series to be negative, is this term. The term where we have only one body, one polymer containing one body only. Okay, and this one taking beta sufficiently large, delta very small. We can show beta, both beta and delta very small. Can show that actually this one is negative. Of the other, thanks to the cluster expansion, this one is positive but very small. In the end, doing of the computation, we can get that result. So we can prove that the characteristic function, the integrants inside of the third integral, can be bounded by the exponential of negative t squared times some constant. Taking k very large, we can show that that expression is very small. Remember that we are talking about t to be smaller than delta times the standard deviation. Okay, so taking this k very large, the integrand, this bound, will be very small, proving that the third integral is also very small. That's it. This is the proof of the third integral. Quickly, let me just finish with the proof of the fourth integral. So for this one, the technique is slightly different. So note that we are talking about t far from 0 now. Okay? The result is almost similar to the previous one. Note that the bound that we have here doesn't depend on t anymore. Okay? Before we have t squared, now we don't have. So we have to be careful, exactly because we are in the region of t that we cannot really apply the same cluster expansion that we developed previously. How to prove this result? Cluster expansion again. But we have to be careful. The main idea of the cluster expansion, we are not using the mere expansion. We don't do +1 - 1 in the one body term. This is the main difference. There's an issue here. If you do the mere expansion only the 2 bodies, we do get some kind of gas expansion, this expression. But the main issue is that this is not the real gas expansion. We can't really apply cluster expansion from this expression, exactly because of this yellow term. This yellow term is not usual in the expression of the gas expansion. We have to get rid of it. How to do that? So we have to remove this yellow part. We just remove by using that result. Thankfully, for the any t far from 0, we can show that the expectation of the PDF, exactly of the yellow part, of the part that we don't want, is bounded by some e to the some power -c. Okay, so basically we are saying that it's bounded by some number that's smaller than 1. Basically, this is what we can do it. This is just some computation, so like a kind of exercise actually. If you just open the definition of this expectation, do some computation. Here we use that the potential is absolutely summable, then we can reach to that constant c. All right, so once that we have this expression, now it's easy. Bound this yellow part by using this inequality, we get this inequality here. And something very nice. Now, once that we remove the yellow part, we get exactly gas expansion again. But this gas expansion doesn't depend on t anymore. Okay? And something important, know that we have a different type of activity function. An activity function that depends on some new weights. It's the same zeta that with activity function that we defined previously, but with this new weight depends on the support of the polymers. But it's not that issue. You can still apply Kotak's price or Fernandez-Procat's criterion so that we can show that the cluster expansion is still absolutely summable. In the end, doing all of the computation, it is possible to show that this gas expansion, this new gas expansion, is at most increasing as exponentially of some constant times the volume, where these constants can be very small, taking delta, or here taking beta, very small. That's it. This basically shows you have here a fight between C and alpha prime, but C is just a constant, alpha can be as small as possible, C wins, the integrand is very small, proving that the last integral is small enough. This proves our results. Here we have some reference, and thank you very much. Oi, Roberto.
The first time when you presented the program,
Here?
the composition of the integral you want to prove.
Ah, this one, ok, tá bom. É isso?
Yeah.
Ok.
So you are proving that the three are very small.
Mm.
So you are basically proving that class CAT cannot be
Yes.
zero.
Yes, you're right. You're right. We get equivalent actually. Yeah, that's correct, Roberto. Oh, yes, Lucas.
Can you consider like the JXY to be like random variable?
Ah, random variables. Of the computation, from my view from now, I guess that's possible. I think we can even use the same computation, I guess. Note that we are not using the ferromagnetism here, not using FKG. So note that the issue to ask to be random or about the model itself is to get a CLT part. So probably we can have randomness in the interaction, like well, we can get the interaction. But the point here is that if you need more, you can prove the implication. But if you want really to prove the local CLT by using this technique, you have to have a CLT, and probably in that case we need to ask something more. That's a good point. Okay, right. So the main point here, know that our result is specifically for the high temperature. So in the region that there is no phase transition, but it's a good point here. If you are taking low temperature in the region that we do have phase transition, we have to really be careful with the central limit theorem. So usually potential or models in general, type of CLT is not that common actually. So in particular, if you should make more sure about the settings, for the 2D nearest neighbor easy model, for the Dobruchin-Tirozzi, we have that implication. However, if you want to have the CLT, we need to consider the extremal Gibbs measure at low temperature.
Because it seems that at the beginning there was a question that the condition depends when you choose the boundary condition. So phase transitions can also depend on that, right? So
Should depend, exactly. It will depend. And that's the main problem here. So if you take the extreme Gibbs measure, this we are starting expecting to have a Gaussian in the end. But if you have a more general settings for different boundary condition, that definitely is much more sensitive, that will interact with inside of the box, probably even CLT might not be true anymore. We have to have a different type of scaling. Oh, yes?
Are there any results like the Donsko's invariance principle, like convergence of Brownian motion in some
Oh, that's a good question. I don't know.
thingy?
I don't know. But good question, Spartans.
I think to apply for a sequence of a scheme.
Yeah, like
Because
some
the
setup
Donsko's
that makes sense.
Mm-hmm.
Yeah, some setup where that makes sense. You have a sequence of boxes and you want to converge the process. Like some simpler setup. Should be true.
Yeah.
Mm.
no more questions? Okay, thank you. Then
funziona.
So, Anatoly, Yambartsev from the USP will discuss matter-antimatter symmetry, a power-free-toy explanation.
Okay. Thank you, Aganardis, for inviting me to share some idea what we are working with. And now, currently, this is a current joint work with Pechersky and Logachev. First of all, I should probably apologize that it's not statistical physics topics. It's more or less stochastic processes area, but I think that it's helpful for conference to see something more out of statistical mechanics. So what we started with Pechersky in some years ago. Yes, we discussed on lunch here the problem of physics phenomena about matter-antimatter asymmetry, and the physics looking for the symmetry, fundamental asymmetry within the law, within the fundamental particles, and we discuss and we say, okay, suppose that there is no asymmetry within the law, there is no asymmetry between particle and antiparticle, and the phenomena that we observe, this matter-antimatter asymmetry, is a result of the competition between matter and antimatter. So, and we decided to construct some we construct a lot of we tried a lot of models, but probably this one is one of last one. Imagine here a number of antimatter particles, here the number of matter particles, and I put one, but it's really grid n. It's you can imagine n. It's volume of universe, or total number of particles and antiparticles in the universe, something like this. Okay, and the dynamics probably here it's more easy to understand, because the number of particle and number of antiparticle, when particle and antiparticle comes, they annihilate. So it means that the number of particles and antiparticle decrease by 1. And if and here one particle antiparticle creates. Probably it was here something more, but I confess that just don't remember. The main part here is the intensity of creation of particle and antiparticle decreases when you stay near the volume of universes. I'm not sure why we put it, because probably because of some expansion of universe and so on. So in any case, here, so we created some random process that reflect the number of particle and number of antiparticle in the universes. It's make some random work here. See,
And with simulation here, yes, it's a result of simulation. So if I started here, very rapidly, quickly, the process go for this line. This line is number is the point of stationary points of the process. Here, if I start here, also, so it's some attractive set of points for this process. So it's some simulation here, and the process go quickly here, and then he started to make some random work near these particles, near this set, equilibrium set. But it was very difficult to see how is the particle move here because of lattice and so on. And but what we see that the frequency or rate of rate, the velocity, how the process change your state, it's something like this. It's a velocity, it's a decrease here, increase here, and decrease here. Okay, so the rate, the process is go more rapidly here, see, and very slow here in this point. So the and no, I change some minute change. No. So and we decided to simplify our model to see only the movement on the line, and even more we decided to consider this process, the process on the integer number 1, 2, and up to n, for example, and the rate transition rate. The process jumped only for neighbors here, and the rate equals if you stay in the state m, and it's not only equal, but they are proportional to the m. We choose this problem to reflect this idea that here the processes go very quickly, and here he go more slowly. So sure, we put some boundary condition here, and it means that the process is continuum time random process, Berf and Derf continuum time random process in integer, and there are a lot of things that we know about these processes. And so the question arises, what is about the asymptotic when n go to infinity? We should put n go to infinity because we interpret it as a size of university. And also some lack of localization. We don't specify very well what does it mean, and we wanted to understand if there exists some type of phenomena or not for this model. We interpret it as a matter prevalence, for example, and localization means also if. So now what we observe is the matter, there is no antiparticles. And what happens if our history is the result of stochastic computation between particle and antiparticle? Probably, if you see the particle prevalence for some time, after some times, the antiparticle can prevalence too. So and if there is no localization phenomena. So and these are was our questions when we started to study these models. So model is not so complicated. Invariant measure it's very quickly we obtain because of Befedov processes here, and you see that the stationary measure is proportional. It's proportional to 1 over m. And it means that with some type of localization phenomena, see for invariant measure, we can obtain. Yes, because if I choose some epsilon time and space here, epsilon is small, we see that if I started to sum summation of this invariant probability here and the summation of invariant probability here, we see that with some it's a log of n, yes. So it's a log of epsilon n, and some of this will be a log of n. It means that really we have some concentration phenomena near the one. So in order to understand the asymptotics, so we need some scalings, and the first scaling we consider, we divided on our process by n. It means that we put our process between 0 and 1 here, and the first thing that we can ask here, see what happens when n go to infinity. See, it's something like it's a law of large number here, what we can see. And the first result we proved that it's really law of large number, and the trajectory of our process, if he started near the point gamma, see, it's will be constant. We doesn't see any large fluctuation for this process. So it means that its process will be near the starting point, I show some why it's happened. It's very simple proof because the process can be represented as a sum of plus and minus 1 during my process, and if I condition the total number of jump of my process, so we can apply the Kolmogorov inequality, for example. It's a maximum of these sums. Yes, it's Kolmogorov inequality, and it's strange, but it was enough to estimate the number of jumps by Poisson process with maximal intensity, maximal intensity n. It was enough for us. N and 1 over n, and it's go to 0. So when we have law of large number, so logically the local large deviation principle appear here, and so we are interested in functional large deviation principle, where we consider the probability of our process, scaled process, to stay near the sum function gamma. Some function gamma, you take a log 1 over n, and with our objective to find the rate function. It's rate functional because gamma it's functional. So I remember that our process between 0 and 1, if he started from some point, it will stay here with great probability. It's time, and what we ask here, and what happen? What is probability to stay near the some function gamma when the process will stay? So when n go to infinity with probability, we know that it's go to 0. and the rate function show the rate, the velocity, how this probability go to 0. It's a if we are interested only in rate function in this, it's it's we call local large deviation principle, and more interesting in large deviation principle because for a large deviation principle, some type of the possibility to solve some type of optimization problem. So I know that my process makes something, and we describe it by some event B. And what is the probability? What about the rate function here? So the rate function will show for us in some optimal way to make this happen. Okay, so it's resolving this problem. Here the possibility to resolve this problem, what especially the large deviation principle means for us. So and how to to resolve it's large deviation principle for stochastic processes or Fenge course. It's our how to say our principal reference here, and probably the best way which describe how to obtain the rate function using Fenge course. It's I found in this paper. One of author it's here, Roberto Fernandez. So I make copy paste from this paper. It's the appendix. It's explained very well how to what we need to do in order to obtain the rate function. So in order to obtain the rate function in this way, with Lagrangian, we need to obtain this. So it should compute a generator for nonlinear semigroup. Ln here it's a generator of our process. Generator which should apply for the function e to the power nf, where f is some function, e to the power nf will be the function, and after that we should multiply this result for inverse e to the minus n divided by n, and this if this the first we should to find this limit. First it's creates some nonlinear semigroup. After that we need to find what it's really a generator of some semigroup. But here, in order to construct, we will consider this generator in this way, where h is we'll call the Hamiltonian for our process, and delta of f it's derivative in our case, for example. Will be then we if I know this function, I take I represent it by Legendre transform, and making an inverse I can find the L, and so I put it here, and this integral of this Lagrangian will be the rate function. So it's the rate function. The only things I wanted to why I show it, I want to show that there exists some gamma point derivative of a gamma divided by gamma. It means, for example, that it's impossible that the rate function will be infinity if we consider some function types this, which go with some derivative to 0. For this type of function, it's impossible. It's really the process will go very slowly here, see, and it's the probability to make this pattern here. It's will be infinity. Yes, so and it means that the derivative should go to 0 together with the gamma if gamma go to 0 here. So it's one of rare, I don't know, case when we can write this functional in explicit form. Also, we make LDP. See, it's in essentially 4 steps that we need to verify here. Verify that it's convergence of sequence, check exponential compact containments, prove that generate the semi-group. It's very technical steps, and I decided to not show here. See, in constructive variational representation for each function, all these steps we proved. It means that we have local we have no only local large deviation principle. It means that we have a large deviation principle, and for example, we can resolve some optimization problem. For example, if my process, if I started from 0, we know that the process will be in 0 here. See, it's by law of large number, and I can ask the following: if I started from 0, see, and in the time t here or 2, I want that my process go away from 0 to this point. What is the optimal path? How to go? What is the optimal path that we will observe in the scaling? The optimal path is parabola. Here, it's also we know how to resolve it. And here another situation. If I start here, it's my mean value. See, and how to if I want to be far from this mean value. See, again the parabola, and here also parabola, but it's not very good. It's a point of top of bottom of parabola here. So and okay, it's like that we resolve the problem, but if I see for the process, it's something like it's my scaling as this one. It means that the t it's some finite values here, n will go to infinity. If I want to interpret my process x as some part of matter or antimatter in the universe, it means that I only observe that the very early universe, because the t is very small in comparing to the n. What does it mean? It doesn't mean that I wanted to put it some time scaling too. And so in order to define this, we decided, so we have a law of large number, large deviation principle, and what more? A central limit theorem. And we decided to see the central limit theorem and trying to find the right space-time scaling. We found that and we decided to generalize a little bit our process again from 1 to n. And if it's my current state, for I jump for neighborhood for the same rate, and this rate will proportional to m to the power alpha. Alpha now it's positive. In our case, here our initial model alpha is equal to 1. So what happened here? We find the right scaling. It's only to write the generator and see if the generator makes sense. And we find this time scaling. So for this time scaling, it's a current. We still check all these results. It's very new, but it seems I say in this way. Yeah. So it seems that it's true. So our process will converge weakly in space of catalog functions to the solution of a stochastic differential equation here. Stochastic differential equation, what we have here is the starting point. We have no drift, yes, and the diffusion portion with its variance is x to the power alpha divided by 2. So it's again it's proportional to x to the power alpha and alpha divided by 2. And f when x is small value near the 0, it means that the diffusive part will be very small. So here here are some technical things that related to the n when we divide it to n with reflection reflection condition in the boundary one, and it seems it's true. And we see that there exist three cases. First of the case when alpha is smaller than 1 and greater than 0. In this case, the solution a differential equation exists. But in the literature, they say that that exists, but they have no uniqueness. And what happened here? If my process if I observe my process up to the time the heating time to 0. There is no here problem. The process exists. It's a unique uniqueness. But after that, there exists various possibility, and the behavior near the 0 that gives non-uniqueness for such processes. But if we consider the process as as a limit of our process, we proved that our process reflect here. So there is no, we can prove that we'll converge for a unique solution with reflection with 0, with absolute reflection with in 0. So it means that it's if our universe corresponds with alpha, we have no chance. Probably for after some times, after some billions, our process will destroy it and will go to antimatter, for example. So what happens in the situation when alpha from 1 to 2? It's more easiest way, because its solution it exists. It's a unique solution for this alpha, and more interesting that for this alpha, the solution will be the following. It makes some fluctuation up to the heating time of 0, and after that the process will stop here. So it means that we found our localization problem. So if our universe corresponds to alpha is equal to 1 with things, so we have we will maintain with the matter. There is no possibility to explode with the antimatter. In this case, it's very there exists also a solution, because it's we only see here from 0 to 1, and but here you see when alpha is sorry greater than 2, it means that we will divide for some very large numbers. It means that the very initial of universe that we consider here. So it means that with this process also we have this diffusion process. But what happened here, that the process never hit the 0. there is no chance for heat to zero for this process. So with some references, I will. So and obrigado pela atenção. It's not statistical physics very well, so question. Buffet-Dose process we studied because there exists another background when we studied the large deviation principle for Buffet-Dose processes that have their, for example, lambda n is proportional to some n to the power alpha, some constant alpha a, and the mi is proportional to n to the power beta b here. So for such processes we studied a long time with large deviation principle for these processes, and the only one way that we cannot prove the local large deviation principle for such processes is when alpha is equal to beta and the a is equal to b. It's exactly this symmetric case that we studied. So with two backgrounds come together, and we decided to study this one. So for the large deviation principle, local large deviation principle that we proved here, we choose some techniques of change of measures, but it doesn't work for symmetric case. So for symmetric case, the large deviation Fengi-Kurz techniques. Yes.
You have to use this.
Yeah, sure. It's this only these techniques that gives us the possibility to resolve this. No, it's a paper of yes, Gibbs on Gibbs. Yes, it's for you. See, it's about the large deviation view on the Gibbs on Gibbs. What does it mean? See, but I confess that only this part I was very excited when we have how to compute the rate function quickly for Markov process.
Okay, thank you very much.
Thank you.
A thought book. I mean,
Yes, it's a whole book.
And very abstract, and you need this.